Part 1. Neasosaurus. Neasosaurus parringtonii is known from fragmentary remains discovered in the 1930s amid the reddish sandstones of the Lifua member, Manda Formation, in southern Tanzania. These bones, chiefly a partial upper arm bone, humerus and several vertebrae, lay unrecognized in museum collections for decades until reanalysis in 2013 identified them as belonging to either the earliest true dinosaur or its closest dinosauriform relative. With an estimated age of around 243 million years, Neasosaurus pushes the origin of dinosaurs potentially into the Middle Triassic, upending previous timelines that placed their rise in the Late Triassic. Its name, meaning Lake Neasa Lizard, honors both the nearby lake and Francis Rex Parrington, the paleontologist who first collected the fossils. Although only scraps remain, these scraps transformed paleontologists' understanding of when and where the first dinosaurs, or their immediate kin, emerged on Pangaea's ancient landscapes. The story of Neasosaurus's scientific recognition spans nearly 60 years. Francis Rex Parrington unearthed the holotype material during expeditions in the early 1930s, but it was not formally named until Sterling J. Nesbitt and colleagues published a full description in 2013. Prior to that, the bones sat in London's Natural History Museum, catalogued but unassigned, mentioned only briefly in Alan J. Charig's unpublished 1956 thesis, and later in a 1967 review under a provisional name. Nesbitt's study reinstated Charig's original intention, formally christening the genus and species and ensuring that Neasosaurus entered the paleontological record as a valid taxon. This long gestation from discovery to description highlights how fragmentary fossils can lie dormant until cladistic and histological advances reveal their true significance. The Lifua member of the Manda Formation, where Neasosaurus was collected, represents sediments laid down in vast floodplains and seasonal wetlands along the southern margin of Pangaea. Biostratigraphic correlation, based on contemporaneous fish, amphibians and other archosaurs, places this layer in the Anisian stage of the Middle Triassic, about 242 million years ago. Some geologists argue the deposits could be slightly younger, Carnian in age, compressing the timeline between Neasosaurus and later dinosaurs to mere millions of years. Resolving this debate requires precise radiometric dating of volcanic ash layers, a task that promises to refine when the dinosaur lineage truly branched away from its reptilian cousins. Neasosaurus's known bones are scant, but telling 3 presacral vertebrae and 3 sacral vertebrae, alongside a single right humerus. The humerus is striking for its elongated delta pectoral crest, more than 30% of the bone's length, a hallmark of dinosaur forelimb musculature. The vertebrae show articulations similar to later dinosaurs, including hyposphene, hypantrum articulations that stiffen the spine. While no skull or hind limb material has yet been definitively linked, the existing elements display a blend of primitive archosaur and derived dinosauriform features, placing Neasosaurus at the very base of the dinosaur family tree. Bone histology of the Neasosaurus humerus reveals rapid, uninterrupted growth, with dense vascular canals and woven fibered bone, characteristics shared with early true dinosaurs. Lines of arrested growth, which mark seasonal pauses in bone deposition, are largely absent, indicating continuous growth over several years. This growth pattern contrasts with slower-growing, sprawling archosaurs of the time and aligns instead with the fast-growing, erect-limbed dinosaurs that later came to dominate terrestrial ecosystems. Such rapid growth likely conferred advantages in predator avoidance and competitive foraging, traits that may have fueled early dinosaur success. Size estimates for Nyasasaurus, extrapolated from vertebral and humeral dimensions, suggest a lightly built animal, roughly 2 to 3 meters in length, and weighing between 20 and 60 kilograms, comparable to a medium-sized dog with a long tail. Its slender form and likely erect posture imply an agile bipedal runner. The floodplain habitats of the Manda Formation would have demanded agility amid shifting river channels and vegetated margins, where Nyasasaurus may have foraged on small vertebrates, insects, and plant material. Its limb proportions hint at an active cursorial lifestyle rather than the sprawling gait of more primitive archosaurs. Phylogenetic analyses have variably placed Nyasasaurus as either the sister taxon to all true dinosaurs or as the earliest branching member within Dinosauria itself. In either position, its existence confirms that the dinosaurian lineage had diversified by the Middle Triassic, significantly earlier than the well-known Late Triassic Eoraptor and Herrerasaurus. This pushes back the origin of key dinosaurian traits, such as rapid growth, upright stance, and specialized limb musculature, to at least 243 million years ago. By occupying this pivotal node, Nyasasaurus illuminates the gradual assembly of the dinosaur body plan. Despite its groundbreaking implications, Nyasasaurus leaves many questions unanswered. No cranial material has yet been found, leaving its diet and sensory capabilities speculative. The precise arrangement of its hind limbs, vertebral count, and pelvic structure await confirmation through new discoveries. Furthermore, resolving the age of its deposits will clarify whether it truly predates other Triassic dinosaurs by 10–15 million years or coexisted alongside them. Each new fossil from the Manda Formation holds the promise of filling these gaps, offering a clearer picture of life on Earth when dinosaurs first began their remarkable reign. Nyasasaurus parringtoni stands as a testament to the power of fragmentary fossils to reshape scientific paradigms. From overlooked museum drawers to the headlines proclaiming the oldest dinosaur, its journey underscores how meticulous re-examination and modern techniques can resurrect silent stones into vibrant stories of evolution. In the slow cadence of geological time, Nyasasaurus marks the dawn of Dinosauria, or its immediate precursors, offering a tantalizing glimpse of the first steps taken by creatures that would one day rule ancient landscapes and inspire wonder millions of years later. Part 2. Acelysaurus. Discovered in the Lifua member of the Middle Triassic Manda Formation in southern Tanzania, Acelysaurus kongwi emerged as a pivotal link between early archosaurian relatives and true dinosaurs. Its remains, first noted in 2007 and formally described in 2010, are preserved within reddish channel mudstones deposited roughly 243 million years ago. This places Acelysaurus among the earliest members of the dinosauriform lineage, predating many well-known late Triassic dinosaurs by nearly 10 million years. The fossils were excavated from bone beds alongside other archosaurs and synapsids, offering a window into a diverse assemblage of reptiles that thrived long before dinosaurs came to dominate terrestrial ecosystems. The genus name combines the Swahili word acely, meaning ancestor or foundation, with the Greek sauros, lizard, while its species epithet kongwi translates to ancient. These appellations underscore Acelysaurus's position near the base of the dinosaur-pterosaur branch of the archosaur family tree. Type material, including a partial left dentary, skull fragments, pectoral and pelvic girdles, limb bones and vertebrae, comes from at least 14 individuals of varying sizes. This abundance of material contrasts sharply with most early dinosauriforms, which are typically represented by isolated bones or single specimens, allowing for a far more complete reconstruction of its anatomy and ontogeny. The paleo-environment of the Manda Formation was characterized by meandering rivers, floodplains, and seasonally wet soils set against a backdrop of a humid monsoonal climate. Fossils of early crocodile-line archosaurs, dicynodonts, cinnobants, and amphibians share these sediments, indicating a richly vegetated landscape with abundant water sources. Volcanic ash layers interbedded with fluvial deposits enhanced fossil preservation, capturing delicate bone and possible soft tissue impressions. Within this setting, Arcellosaurus would have navigated a patchwork of forests and open areas, exploiting resources unavailable to its sprawling semi-aquatic contemporaries. At an estimated 1.5 to 3 meters in length and weighing perhaps 10–20 kilograms, Arcellosaurus possessed a lightweight, gracile build. Limb proportions indicate a facultatively quadrupedal gait, with forelimbs only slightly shorter than the hind limbs. Long, slender limbs suggest it could shift seamlessly between four- and two-legged locomotion, possibly adopting a bipedal stance for rapid dashes or upright browsing. Its tail was long and held horizontally, counterbalancing the body and aiding in agile maneuvering amidst dense underbrush or along riverbanks. Cranial anatomy reveals a beak-like snout with a toothless premaxilla, followed posteriorly by a series of small leaf-shaped teeth. The downturned jaw tip and lack of incisiform teeth hint at a primarily herbivorous diet, with teeth suited for cropping vegetation rather than slicing flesh. Wear facets on tooth surfaces suggest occasional omnivory, perhaps supplemented by insects or small vertebrates. This mixed feeding strategy would have conferred resilience in fluctuating environments, allowing Arcellosaurus to take advantage of seasonal plant growth and opportunistic animal prey. Although no direct integument impressions are known for Arcellosaurus, its close relationship to other early dinosauriforms raises the possibility of filamentous or proto-feather structures. Comparisons with Silosaurus and early pterosaur relatives, many of which display feather-like coverings or melanism evidence, support the hypothesis that Arcellosaurus may have borne primitive filaments for insulation or display. Such integument would align with the high metabolic rates inferred from bone histology, indicating active, warm-blooded physiology that benefited from dermal insulation in a variable climate. The discovery of Arcellosaurus has profound implications for archosaur evolution. As a basal member of Silosauridae, a clade sister to dinosaurs, it documents a rapid diversification of the bird and pterosaur line archosaurs of Emetotarsalia in the Middle Triassic, a pattern previously only clear among crocodile-line archosaurs. This suggests parallel radiations in both branches, challenging models that placed dinosaur origins squarely in the late Triassic. Arcellosaurus therefore occupies a critical node, illuminating how major archosaurian lineages diverged and adapted to distinct ecological roles. Yet many mysteries remain. No juvenile or hatchling specimens have been identified, leaving early growth stages and developmental shifts speculative. The extent and nature of its potential filamentous covering await discovery of skin impressions or associated soft tissues. Likewise, the precise paleoecological interactions between Arcellosaurus and co-occurring archosaurs, synapsids and amphibians remain poorly resolved. Continued fieldwork in the Manda Formation and refined radiometric dating promise to sharpen its chronological placement and ecological context. Arcellosaurus Conway stands as a testament to the mosaic nature of evolution, a creature bearing both primitive archosaur traits and derived dinosauriform innovations. Its blend of quadrupedal and bipedal adaptations, herbivorous dentition, and possible proto-feather integument offers a vivid snapshot of Archosauria's early experimentation. As research advances, Acyllosaurus will remain a focal point for understanding the dawn of dinosaurian and pterosaurian diversity and the ecological dynamics of Triassic ecosystems well before the age of dinosaurs truly began. Part 3. Eoraptor. Eoraptor lunensis represents one of the most complete and informative skeletons among the earliest dinosaurs residing in the Esquigualas formation of northwestern Argentina. Dating to about 231 million years ago, Eoraptor lived on lowland floodplains marked by meandering rivers, seasonal wetlands and forests of seed ferns, horsetails and early conifers. Its nearly intact skeleton was rescued from the Val de la Luna, Valley of the Moon, in 1991 and described in 1993, providing unprecedented clarity about dinosaur origins. At roughly 1 meter in length and weighing around 10 kilograms, Eoraptor's graceful form combined both primitive archosaur traits and features foreshadowing later theropods and sauropodomorphs. The skull of Eoraptor reveals clues to its feeding ecology. The slender snout bore 4 slender teeth in the premaxilla and over 18 in the maxilla, exhibiting heterodontia. Its front teeth were recurved and serrated, akin to small theropods, while the posterior jaw bore leaf-shaped teeth, reminiscent of early sauropodomorphs, an unusual mix suggesting omnivory. Wear patterns and microwear on the teeth indicate Eoraptor consumed both small vertebrates and plant matter, making it one of the first known omnivorous dinosaurs. This dietary flexibility would have conferred a significant advantage in the dynamic Triassic landscapes, where food availability fluctuated with seasonal cycles. Limb proportions demonstrate that Eoraptor was a nimble bipedal runner. The hind limbs were long and slender, with a tibia exceeding femur length, an adaptation for speed, while the forelimbs remained fairly short, but capable of grasping. Its hands featured 5 digits, the first 3 tipped with recurved claws poised for capturing small prey or manipulating vegetation. The creature likely shifted seamlessly between quadrupedal foraging and bipedal sprinting, using its long tail as a counterbalance. Estimated speeds may have reached up to 30 kilometers per hour, enabling it to evade larger predators or swiftly pounce on insects, small reptiles and carrion. Eoraptor's vertebrae possess a mix of plesiomorphic and derived characteristics. The cervical and dorsal vertebrae were spool-shaped with prominent zygapophyses for strong muscle attachment, supporting an upright posture. Sacral vertebrae joined firmly to the pelvis, stabilizing the hindquarters during rapid locomotion. Pneumatic foramina in the vertebrae hint at early stages of an avian-style respiratory system, allowing lighter bones and improved oxygen exchange. This blend of traits underscores how early dinosaurs were already experimenting with the biomechanical innovations that would later propel giants like Brachiosaurus and swift predators such as Velociraptor. Fossil preservation in the Esquigualas formation is exceptional due to periodic volcanic ash falls that rapidly smothered and mineralized organic remains. This Lagostetta quality preservation includes not only bones but occasional soft tissue impressions, enabling detailed reconstructions of early dinosaur biology. Eoraptor specimens are often found alongside other basal dinosaurs like Herrerasaurus and Panphasia, as well as cynodonts and amphibians, illustrating a complex ecosystem. Such co-occurrence reveals niche partitioning. Herrerasaurus dominated as the apex predator, while Eoraptor occupied a mesopredator or opportunistic niche, feeding at multiple trophic levels. Growth studies using histological sections of Eoraptor's limb bones show rapid deposition of woven fibered bone with minimal lines of arrested growth. This indicates a high metabolic rate and fast juvenile development, reaching adult size in as little as 2 years. The combination of rapid growth, active locomotion, and omnivory suggests Eoraptor maintained an endotherm-like physiology, challenging the traditional view of dinosaurs as strictly ectothermic. Its life history strategies mirror those of many modern birds and mammals, with precocial offspring capable of early independence and rapid growth to escape predation. Phylogenetically, Eoraptor's mix of traits once led to its classification as a basal theropod, but later analyses support its placement as a basal sauropodomorph, or even as a very early divergent saurischian, branching off before the theropod, sauropodomorph, split. Its mosaic anatomy exemplifies the difficulty of drawing sharp lines early in dinosaur evolution, when the first radiations explored multiple ecological strategies in parallel. Whether Eoraptor is viewed as an early theropod or sauropodomorph, its combination of features provides a key snapshot of the ancestral dinosaur condition. Despite its pivotal role in reconstructing dinosaur origins, Eoraptor still holds mysteries. No skin impressions have confirmed the presence or absence of protofeathers. However, its phylogenetic position alongside other Triassic dinosaurs that bore simple filaments makes it plausible Eoraptor carried insulating integument. Direct evidence remains elusive, but ongoing excavations and refinements in preparation methods may one day reveal traces of soft tissues. Discoveries of additional specimens, especially juveniles, could further clarify ontogenetic changes in anatomy and behavior. Eoraptor lunensis remains one of the most significant finds in vertebrate paleontology, a diminutive dawn plunderer whose remains illuminate the formative chapters of dinosaur evolution. In its graceful skull, agile limbs, and mixed dentition, the earliest saga of Earth's dominant terrestrial vertebrates unfolds, a tale of experimentation, adaptation, and ecological innovation that set the stage for the Mesozoic's unparalleled dinosaurian drama. Part 4. Herrerasaurus. Herrerasaurus isigualastensis represents one of the earliest large carnivorous dinosaurs, roaming the floodplains of what is now northwestern Argentina during the late Triassic Carnian, around 231 million years ago. Its fossils hail from the Isigualasta Formation, a landscape once dominated by braided rivers, lush vegetation, and active volcanoes. Herrerasaurus stood about 3 to 4 meters in length and weighed close to 200 kilograms. With a long tail and powerful hind limbs, it had a sleek build designed for speed and agility. Though later outshined by the more famous predators of the Jurassic and Cretaceous, it remains a crucial piece of the evolutionary puzzle, helping define what the earliest dinosaurs looked like and how they lived. The discovery of Herrerasaurus stretches back to the late 1950s, when a local herdsman named Victorino Herrera came across its bones. Argentine paleontologist Osvaldo Reig formally described the species in 1963, naming it in Herrera's honor. For decades, scientists debated where exactly it belonged in the dinosaur family tree. It seemed too primitive to be a classic theropod, yet too specialized to be completely outside of Dinosauria. The debate was largely settled in the late 1980s, when nearly complete fossils, including a skull, were unearthed, revealing a creature that sat at the very base of the theropod lineage. It was among the first to showcase traits that would later define the great meat-eaters of the Mesozoic. The skull of Herrerasaurus reveals much about its feeding habits and evolutionary status. It was elongated and filled with serrated, curved teeth ideal for slicing through flesh. The upper and lower jaws were loosely hinged at the back, allowing for some degree of movement, an early precursor to the kinetic skulls seen in some later theropods. Openings in the skull not only lightened its weight, but also allowed space for strong jaw muscles. This combination of lightness and power meant Herrerasaurus could bite quickly and efficiently, a necessity in an environment full of nimble prey and larger predators. Herrerasaurus moved with a purpose-built frame for speed. Its long legs and relatively small forearms echo the body plans of later pursuit predators. The structure of its hips and limbs suggests it was a digitigrade runner, standing on its toes like a modern-day bird or cat. A stiffened tail likely acted as a dynamic counterbalance, allowing tight turns while maintaining momentum. Trackways found in similar aged rocks match the size and gait of Herrerasaurus, giving further credence to its role as a fast, active hunter. It was not the largest animal in its habitat, but its speed made it a dominant force. The forelimbs of Herrerasaurus, although shorter than its legs, were strong and armed with claws that could grasp and slash. It had 3 primary fingers, each tipped with a curved claw, while a vestigial 4th digit hung loosely. Muscle attachment points in the shoulder and arm bones suggest it could quickly draw its arms inward, useful for grabbing prey or perhaps defending itself from rivals. Its claws were not just tools of aggression, but may have also played a role in feeding, allowing the dinosaur to tear meat or hold struggling animals in place while delivering a killing bite. Dietary evidence places Herrerasaurus squarely in the carnivorous camp. Tooth marks found on bones of other small animals indicate active predation rather than scavenging. Some bones even show signs of intraspecific conflict. Teeth marks from another Herrerasaurus, hinting at social interactions that included fighting over territory or mates. Its prey likely included small reptiles, early mammals, and other proto-dinosaurs. Its role as a top predator in the Isquigualasto ecosystem made it a key player in maintaining ecological balance during a time when dinosaurs were only just beginning to rise in dominance. Clues from its bones also provide a glimpse into its behavior. Fossils show signs of healed injuries, indicators that Herrerasaurus engaged in combat but survived to tell the tale. Its eye structure suggests it may have had good vision, possibly with overlapping fields of view for depth perception. Such traits would have made it an efficient and precise hunter. Moreover, its relatively small brain case, while not suggesting great intelligence by modern standards, was consistent with an active predatory lifestyle, likely supported by keen senses and quick reflexes. From an evolutionary standpoint, Herrerasaurus stands as a transitional figure. It shared traits with both more primitive archosaurs and more derived theropods. Its hip structure, skull anatomy, and limb proportions offer a snapshot of dinosaur evolution at a formative stage. The mix of basal and derived traits makes it a mosaic species, preserving information about the earliest adaptations that would later define the great predators of the Jurassic and Cretaceous. Herrerasaurus is not just a dinosaur, it is a bridge between ancient reptiles and the creatures that would later dominate the Earth. Despite its importance, many questions about Herrerasaurus remain. No skin impressions have been found, leaving its outer appearance largely speculative. Some theories suggest it might have had proto-feathers or a scaly hide, depending on its exact placement in the dinosaur family tree. Juvenile specimens are rare, making it hard to determine how it grew or changed with age. New discoveries in Argentina and other Triassic deposits may eventually provide more insights. Until then, Herrerasaurus remains one of the most fascinating windows into the dawn of the dinosaurs, an agile predator from a world just beginning to change. Part 5. Styracosaurus. Styracosaurus price stalked the late Triassic floodplains of southern Brazil around 225 million years ago, its presence captured in the sandstone of the Santa Maria Formation. At roughly 2 meters in length and weighing some 30 kilograms, it was one of the smaller predators of its time, yet its sleek build and muscular hind limbs made it a swift and capable hunter. Small sites preserving partial skeletons reveal an agile creature whose anatomy bridged the gap between the sprawling archosaurs and the upright dinosaurs that would come to dominate the next era. Its discovery in the 1930s by paleontologist Llewellyn Ivor Price ignited decades of debate over early dinosaur evolution, cementing Styracosaurus as a keystone in understanding how dinosaurs first diversified. The skull of Styracosaurus was elongated and lightly built, featuring sharp, backward-curving teeth perfectly suited for grasping and slicing flesh. The lower jaws were slender, allowing a wide gape, while the temporal fenestrae, holes behind the eye sockets, lightened the skull and provided attachment points for strong jaw muscles. Despite its modest size, the dinosaur could clamp down on small vertebrates and insects with surprising force. Microscopic examination of tooth wear suggests a diet that included both smaller prey and opportunistic scavenging, hinting at dietary flexibility in a world where food sources could shift dramatically with the seasons. Styracosaurus's powerful hind limbs enabled it to sprint across open ground with bursts of speed estimated at up to 30 kilometers per hour. Its femur and tibia were long and slender, while the ankle joint was structured for a digitigrade stance, allowing it to stand on its toes like modern birds. The tail was stiffened by elongated bony processes, acting as a counterbalance during high-speed turns. Footprints found in coeval formations bearing a three-toed pattern match its estimated size and gait, providing compelling evidence for its locomotor prowess. These tracks, coupled with skeletal anatomy, point to a predator that relied on quick pursuit and agile maneuvers to capture prey. Although primarily bipedal, Styracosaurus retained relatively robust forelimbs ending in three-fingered hands, each digit tipped with a recurved claw. Muscle scars on the humerus and shoulder girdle indicate that its arms were capable of powerful, if not lengthy, strokes likely used to grasp or slash at struggling prey once caught. The combination of strong arms and grasping claws suggests a two-stage killing strategy: rapid pursuit followed by a disabling grip before delivering a fatal bite. This hybrid approach underscores the transitional nature of early theropods, experimenting with both speed and manual dexterity. The paleo environment of the Santa Maria Formation was a mosaic of river channels, seasonal wetlands, and forested patches of ferns and primitive conifers. Frequent volcanic ash falls blanketed the floodplain, rapidly preserving even delicate bones. Other inhabitants included the sail-backed synapsid Hyperodapodon, early rhynchosaurs, and other primitive dinosaurs like Herrerasaurus. In such a competitive ecosystem, Styracosaurus carved out a niche as a mid-level carnivore, avoiding direct competition with larger apex predators by focusing on smaller, more elusive prey. Its agility allowed it to exploit both open and vegetated terrains, slipping through underbrush to find its quarry. Phylogenetically, Styracosaurus belongs to the Herrerasauridae, a group of early Saurischian dinosaurs whose precise placement remains debated. It exhibits a blend of primitive features, such as only two sacral vertebrae connecting the pelvis to the spine, and derived traits, including hollow limb bones that reduced weight. This mosaic anatomy challenges simple narratives of dinosaur evolution, demonstrating that key adaptations for speed and carnivory appeared early and independently in multiple lineages. As one of the few well-represented Triassic theropods, Staurikosaurus continues to refine our understanding of how true dinosaurs emerged from their archosaur ancestors. Growth patterns in Staurikosaurus are illuminated by bone histology, which reveals rapid deposition of woven fibered bone during juvenile stages, transitioning to more organized lamellar bone in adults. This rapid growth likely allowed young individuals to quickly attain a size less vulnerable to predation. Lines of arrested growth, markers of seasonal slowdown, are rare, suggesting that Staurikosaurus experienced relatively stable climates or maintained activity year-round, further hinting at an elevated metabolic rate. Such findings align with the broader picture of active, fast-growing early dinosaurs adapting to diverse Triassic environments. Despite significant discoveries, many mysteries about Staurikosaurus remain. No skin impressions have been found to indicate whether it bore scales, proto-feathers, or a combination of both. Juvenile specimens are exceedingly rare, leaving gaps in understanding how its proportions and hunting strategies changed with age. Likewise, the exact nature of its social behaviors, whether solitary or pack-oriented, remains speculative, though trackway groupings of similar-sized theropods hint at possible social interactions. Future excavations and advanced imaging techniques hope to unveil these secrets from beneath the red sands of Brazil. In sum, Staurikosaurus priesi stands as a testament to the dynamic experimentation of early dinosaur evolution. Its blend of speed, strength, and adaptability reveals a predator finely tuned to its world. A world in flux as Pangaea rifted and climates shifted. With each new find, Staurikosaurus reminds us that the origins of dinosaurs were neither simple nor linear, but a tapestry woven from countless adaptations and chance discoveries, preserved for us to rediscover millions of years later. Part 6. Saturnalia. Saturnalia tupiniquim roamed the floodplains of southern Brazil approximately 233 million years ago, its lightweight frame darting among early conifers and ferns. The name Saturnalia evokes the season of celebration in its homeland, while Tupiniquim honors Brazil's indigenous peoples. As one of the earliest known sauropodomorphs, this diminutive dinosaur measured barely 1.5 meters from snout to tail and weighed less than a modern turkey. Yet within its slender skeleton lay the first stirrings of the colossal long-necked giants that would dominate Jurassic landscapes. Its fossils, preserved in the Santa Maria Formation's reddish mudstones, offer a rare snapshot of Triassic life, capturing an evolutionary moment when dinosaurs were only beginning to explore new ecological niches. Unearthed in the late 1990s by a team combing the walled Sanger exposures, Saturnalia was identified from 3 partial skeletons scattered across a broad swath of floodplain deposits. Rapid burial in silt-laden floods ensured exquisite preservation of vertebrae, limb bones, and portions of the hips. Volcanic ash layers interbedded with river sediments occasionally sealed carcasses, protecting delicate structures from scavengers. The discovery site's seasonal rivers and ephemeral lakes created an ideal setting for fossilization, preserving not just bones but the very contours of this small dinosaur's life. Its growth rings, muscle attachment scars, and even subtle features hinting at cartilage shape. The hind limbs of Saturnalia were a study in cursorial refinement. The tibia extended slightly longer than the femur, a hallmark of fast-running animals, while the ankle joint exhibited a hinge-like structure for efficient foot strike. Powerful thigh muscles anchored to an expanded hip socket propelled each stride, and the long whip-like tail acted as a dynamic counterbalance. Together, these adaptations enabled quick bursts of speed ideal for evading larger predators or navigating the shifting banks of Triassic streams. Small three-toed footprints discovered nearby match Saturnalia's proportions, confirming it moved with a light, bounding gait rather than a lumbering trill. Contrasting its kinetic hindquarters, the skull of Saturnalia was modest in size but rich in nuance. Jaw fragments reveal leaf-shaped teeth, suited for cropping tough vegetation, yet occasional serrations and wear patterns suggest occasional insect consumption or scavenging on carcasses. Micro-wear scratches point to a varied diet: leaves, stems, and perhaps small invertebrates, illustrating dietary flexibility that would have been advantageous when plant availability fluctuated with monsoonal rains. The slender snout and forward-facing orbits hint at precise bite placement, allowing Saturnalia to nip branches or capture fleeting prey with equal facility. Forelimb morphology further underscores Saturnalia's transitional status. Though shorter than its hind legs, the arms ended in dexterous hands with curved claws. Muscle scars on the humerus and forearm indicate sufficient strength for grasping, possibly to pull down low branches or secure food items. Some researchers propose that juveniles used their forelimbs more actively for climbing or probing, while adults relied chiefly on speed. This duality of function, fleet-footed running combined with manual dexterity, reflects an evolutionary experimentation in limb use that would later diverge into fully quadrupedal sauropods and highly specialized theropods. The Santa Maria ecosystem was a tapestry of Triassic life, where Saturnalia shared its world with early theropods like Styracosaurus, armored atosaurs, and hoofed decenodonts. Towering ferns and primitive cycads formed dense understories, punctuated by stands of conifer relatives. Seasonal floods transformed the landscape, creating shallow lakes rich in fish and amphibians. Within this mosaic, Saturnalia likely inhabited both open and wooded areas, its modest size allowing access to forage beneath low vegetation. Fossilized plant debris and pollen grains from the same strata reveal a lush but dynamic environment that shaped evolutionary trajectories across multiple vertebrate lineages. Phylogenetic analyses place Saturnalia near the base of Sauropodomorpha, in a grade just below the true sauropods. Its mix of primitive archosaur traits, such as a less specialized wrist, and derived characters like an enlarged delta pectoral crest, reflects a mosaic evolution of body plans. The pelvis retains archaic features, while the limb bones show early signs of the robust columnar limbs that would bear the massive weight of Jurassic giants. This blend of features in a single genus underscores how the earliest dinosaurs experimented with diverse anatomical solutions long before the classic sauropod morphology coalesced. Insights into Saturnalia's growth patterns come from bone histology, which reveals rapid juvenile growth with a woven fibered bone matrix and minimal growth line interruptions. Within a few years, individuals reached near adult size, a strategy that reduced vulnerability to predators and allowed early maturation. As growth slowed, the bone tissue shifted to a more orderly lamellar structure, reflecting an energy trade-off favoring long-term maintenance over rapid size increase. Such accelerated early development parallels growth strategies in many modern birds and mammals, suggesting that high metabolic rates were established early in dinosaur evolution. Despite its critical place in the dinosaur family tree, Saturnalia carries mysteries yet unsolved. No skin or feather impressions have been discovered, leaving its integument speculative. Scales, proto-feathers, or a combination may have cloaked its slender body. Its social behavior remains enigmatic. While trackways hint at small group movement, direct evidence of nesting or parental care is absent. Future excavations and refined imaging techniques may uncover juvenile specimens or egg clutches, shedding light on its reproductive strategies. Until then, Saturnalia stands as a testament to the rich experimentation of Triassic dinosaurs, a small but mighty herald of the vast sauropod lineages to come. Part 7. Panphagia. Panphagia protos emerged from the twilight of the Triassic. Its remains unearthed in the Isquigualesto Formation of northwestern Argentina, dated to roughly 231 million years ago. Its name, meaning all-eating pioneer, reflects the unique dentition that baffled paleontologists upon its discovery in 2009. Measuring about 1 meter in length and weighing scarcely 10 kilograms, Panphagia occupied a pivotal spot near the base of the sauropodomorph lineage. Its discovery expanded the diversity of early dinosaur ecosystems, revealing that the first sauropodomorphs were experimenting with omnivory long before the colossal herbivores of later periods appeared. The holotype consists of a partial skeleton, including significant portions of the skull, neck vertebrae, shoulder girdle, and limb bones, offering a remarkably clear picture of its anatomy. The skull is slender yet robust, featuring a mix of sharp recurved teeth at the front and broader, leaf-shaped teeth posteriorly. This heterodont arrangement suggests a diet that encompassed both tender foliage and small animals or insects, granting Panphagia flexibility in resource-scarce environments. Where facets on the teeth indicate it processed food with side-to-side jaw movements, a feeding strategy more commonly associated with later sauropodomorphs. Panphagia's limb proportions speak to a creature adapted for both speed and delicate manipulation. Its hind limbs were elongated, with a tibia nearly matching the femur in length, hinting at an ability to sprint or flee when threatened. The pelvis and ankle joints show adaptations for an erect bipedal posture, allowing the torso to remain balanced over the hips. Forelimbs, although shorter, retained a degree of dexterity. Long, slender fingers bearing curved claws may have been employed for grasping low vegetation or capturing small prey. The combination of cursorial sophistication and manual utility positioned Panphagia as a versatile forager. The neck and back vertebrae reveal a lightweight yet sturdy spine, capable of supporting quick head movements and agile turns. Cervical vertebrae display broad neural spines and well-defined articulations, allowing a wide range of motion to inspect the environment or snatch passing insects. Dorsal vertebrae are elongated and bear hollowed-out chambers that reduced weight without sacrificing strength, an architectural hallmark that would later be magnified in the giant sauropods. This early experimentation with skeletal pneumatization hints at respiratory and metabolic innovations that underpinned dinosaur success. Panphagia inhabited a dynamic floodplain ecosystem characterized by seasonal rivers, volcanic ash beds, and lush vegetation. It shared its world with contemporaries such as Eoraptor, Herrerasaurus, and Dinosaurs, forging a community in which early dinosaurs and their archosaur kin coexisted. Occasional ash falls buried the floodplain under fine volcanic dust, preserving delicate bones in lifelike positions. Pollen and plant fossils from the same strata paint a picture of ferns, horsetails, and primitive conifers, providing an abundant but fluctuating buffet for an opportunistic feeder like Panphagia. Histological analysis of Panphagia's limb bones reveals rapid juvenile growth, evidenced by dense vascular canals and minimal growth line interruptions. Such accelerated development would have provided a swift entry into adulthood, reducing the vulnerable juvenile phase. As the individual matured, bone tissue displays a shift to more organized lamellar structure, signifying a tapering growth rate and allocation of energy toward maintenance rather than size increase. This growth strategy parallels that seen in both other early dinosaurs and modern birds, suggesting an early establishment of high metabolic rates in the dinosaur lineage. Phylogenetic studies consistently nest Panphasia near the base of Pantongymorpha, a clade encompassing true sauropodomorphs and their closest relatives. Its primitive traits, such as a four-fingered hand and certain pelvic characteristics, recall ancestral Saurischians, while its advanced dentition and limb modifications foreshadow the herbivorous giants of the Jurassic. This mosaic of features underscores the gradual assembly of the sauropodomorph blueprint, with Panphasia representing a critical transitional stage in which feeding strategies and locomotor adaptations coalesced into a successful evolutionary package. Despite the clarity its fossils provide, Panphasia still holds mysteries. No direct evidence of skin or filamentous coverings has been found, leaving its outer appearance open to interpretation. Scales, proto-feathers, or a combination may have cloaked its body. Its social behavior remains speculative, though trackways of similar early dinosaurs suggest occasional group movement. Whether Panphasia nested in hidden colonies or led a solitary life is unknown. Each new excavation in Triassic Argentina carries the promise of unearthing additional specimens that could illuminate these aspects of its biology. Panphasia protos stands as a testament to the ingenuity of early dinosaurs, showcasing how selective pressures shaped novel forms and behaviors at the dawn of the dinosaur era. Its blend of omnivorous dentition, bipedal agility, and rapid growth paints a portrait of an adaptable pioneer exploring new ecological avenues. As research continues, Panphasia will remain a cornerstone in unraveling the origins of sauropodomorphs and the broader narrative of dinosaur evolution during the Triassic. Part 8. Pampodromeus. Pampodromeus barberenae lived during the Carnian stage of the late Triassic, roughly 233 million years ago, in the region that is now Rio Grande do Sul, Brazil. Its fossils hail from the upper Hyperodapadon assemblage zone of the Alimoa member in the Santa Maria Formation, a landscape then dominated by braided rivers and seasonal floodplains. The holotype specimen, UL Broad TVT016, consists of a nearly complete but disarticulated skeleton, including most of the skull bones and lower jaws, vertebrae from the back to the tail, elements of both the shoulder and pelvic girdles, and portions of the forelimbs and hind limbs. This abundance of material has made Pampodromeus one of the best-known early sauropodomorphs, shedding light on the dawn of long-necked herbivorous dinosaurs. The skull of Pampodromeus was slender and pointed, equipped with a heterodont dentition that hints at a versatile diet. 4 teeth in the premaxilla were small and unserrated, possibly suited for nipping soft vegetation, whereas the maxilla and lower jaw bore about 20 serrated, leaf-shaped teeth ideal for slicing tougher plant fibers or small prey. Where facets on these teeth indicate lateral jaw movements, suggesting the first stages of herbivorous processing even in this primitive form. Such dietary flexibility would have been advantageous in the fluctuating Triassic ecosystems, allowing Pampodromeus to exploit both plant and animal resources. Limb proportions reveal a creature built for speed and agility. The tibia was noticeably longer than the femur, a hallmark of cursorial animals, and the metatarsals were elongated and slender. The ankle joint permitted a digitigrade stance, enabling Pampodromeus to sprint across open ground or weave through vegetation at rapid pace. Muscle attachment sites on the pelvis and femur indicate robust thigh musculature capable of powerful strides, while the tail, comprised of more than 30 vertebrae, acted as a dynamic counterbalance to maintain stability during high-speed turns. Forelimb anatomy tells a complementary story of grasping and manipulation. Though shorter than the hind limbs, the arms ended in hands with elongated fingers tipped by moderately curved claws. These structures suggest an ability to grasp vegetation or small prey items, and possibly to use the forelimbs in balance or low-level browsing. The shoulder girdle, with its well-developed scapular blade and robust humerus, indicates sufficient musculature for coordinated forelimb movements, an early precursor to the broad range of arm functions seen in later dinosaurs. The vertebral column of Pampodromeus exhibits both strength and lightness. Dorsal vertebrae bear tall neural spines for muscle and ligament attachment, supporting an upright trunk posture. In contrast, the centrum faces show shallow excavations hinting at the beginnings of skeletal pneumatization, air-filled spaces that would later become extensive in giant sauropods. Sacral vertebrae fuse firmly to the ilium, providing a stable platform for powerful hind limb muscles, while caudal vertebrae become progressively more slender toward the tail tip, maintaining flexibility without compromising support. Paleo-environmental evidence from the Santa Maria Formation paints a vivid backdrop for Pampodromeus's life. Seasonal rains fed braided rivers that periodically flooded vast plains, depositing nutrient-rich sediments that fostered dense fern and horsetail undergrowth alongside early conifer groves. Volcanic ash falls blanketed the landscape at intervals, preserving entire communities in fine detail. Coexisting fauna included small carnivorous theropods, armored dinosaurs, and herbivorous cynodonts, creating a competitive and dynamic ecosystem in which Pampodromeus's adaptive versatility proved crucial for survival. Growth studies using bone histology reveal rapid juvenile development in Pampodromeus. Woven fibered bone with abundant vascular canals marks early growth phases, indicating accelerated metabolism and quick attainment of a size less vulnerable to predation. As individuals matured, bone tissue patterns shift toward more organized lamellar bone, signaling a slowdown in growth rate once adult proportions had been reached. These patterns mirror those observed in later dinosaur lineages and modern birds, suggesting that elevated metabolic strategies originated very early in dinosaur evolution. Phylogenetic analyses consistently recover Pampodromeus as a basal sauropodomorph, though its exact relationships with contemporaries like Saturnalia and Pampasia remain unsettled. It shares primitive traits, such as a relatively short thigh bone and only 2 sacral vertebrae with early dinosauromorphs, while exhibiting derived features of sauropodomorphs, including dentition suited for plant processing and limb proportions favoring bipedal running. This mosaic anatomy underscores the gradual assembly of the sauropodomorph body plan, documenting a moment when herbivory and high-speed locomotion began to intertwine. Despite the wealth of skeletal material, Pampodromeus's outer appearance and behavior remain subjects of speculation. No direct skin or filament impressions have been found, leaving open the possibility of scales, simple filamentous coverings, or a combination. Social behavior also eludes clarity. However, trackways from the same formation hint at gregarious movement, by similarly sized dinosaurs. Each new discovery in the Triassic strata of Brazil holds the promise of further illuminating the life appearance, ecology, and evolutionary significance of Pampodromeus, a small dinosaur with an outsized role in the story of sauropodomorph origins. Part 9. Buriolesti. Buriolesti schultzi lived during the Carnian stage of the late Triassic, roughly 233 million years ago, in what is now the Rio Grande do Sul region of southern Brazil. Its fossils were discovered in the Santa Maria Formation, a site renowned for preserving some of the earliest dinosaurs and their relatives. Named in 2016 in honor of Brazilian paleontologist Sergio Buriol, Buriolestes holds the distinction of being one of the most basal sauropodomorphs known, a tiny precursor to the giant long-necked dinosaurs of later eras. Though no larger than a medium-sized dog, this little robber provides a crucial window into the dawn of dinosaur evolution. The holotype specimen of Buriolestes includes a nearly complete skeleton, a skull with lower jaws, vertebrae spanning the neck to the tail, portions of both limb girdles, and nearly all of the forelimb and hindlimb bones. Its excellent preservation owes much to rapid burial in fine floodplain sediments, which guarded even the delicate bones of the hands and feet from scavengers. The skeleton's discovery alongside bones of the early dinosauromorph, Ixalarpeton, highlights a diverse community of small predators and omnivores experimenting with different lifestyles at the twilight of the Triassic. The paleo-environment of the Santa Maria Formation was shaped by seasonal rivers and ephemeral lakes, surrounded by lush vegetation that included tree ferns, horsetails, and primitive conifers. Volcanic ash layers interspersed within floodplain mudstones helped entomb local fauna in moments, preserving fine anatomical details. Buriolestes would have navigated a landscape where waterholes attracted prey and predators alike, and sudden floods or ashfalls could quickly entrap unsuspecting animals, offering paleontologists snapshots of ancient food webs. Anatomically, Buriolestes was built for agility. Its body measured about 1.3 meters in length and weighed roughly 10 to 15 kilograms. The limbs were slender yet robust, with a tibia slightly longer than the femur, an indication of cursorial specialization suited for swift running. The tail was long and whip-like, stiffened by elongated processes that acted as a dynamic counterbalance. This combination of speed and balance suggests Buriolestes relied on rapid bursts of motion to snatch small prey or evade larger predators rather than brute strength. The skull of Buriolestes was low and narrow, with a short snout and large eye sockets. The jaws housed almost 40 small, recurved teeth, each serrated for gripping and slicing. Tooth wear patterns show microscopic gouges consistent with a diet of small vertebrates or arthropods, while occasional blunt wear hints at scavenging on tougher material. The slender lower jaw could open wide, enabling it to swallow modestly sized prey whole. These dental features paint a picture of a small but capable carnivore, not yet specialized but opportunistic. A landmark study of Buriolestes provided the first complete endocast, the internal cast of the brain case, for an early dinosaur. The endocranial cavity reveals small olfactory bulbs and an elongated olfactory tract, suggesting a keen sense of smell. A well-developed flocculus of the cerebellum indicates refined balance and head stabilization during rapid movement. Contrasted with the enlarged regions seen in later sauropodomorphs, these primitive brain features confirm Buriolestes as an active, agile hunter at the base of the sauropodomorph lineage. Locomotor anatomy further underscores its active lifestyle. The pelvis and hip socket are streamlined for efficient muscle attachment, while the foot bones form a graceful three-toed structure with slender metatarsals. Trackways attributed to similar Triassic theropods reveal stride lengths consistent with running speeds exceeding 25 kilometers per hour. Such mobility would have allowed Buriolestes to traverse floodplain channels swiftly, exploiting both terrestrial prey and carrion while minimizing exposure to larger archosaurian predators. Ecologically, Buriolestes occupied a unique niche. It was neither the top predator nor a strict herbivore. Instead, it thrived as a small carnivore omnivore at a time when dietary experimentation was rife among early dinosaurs. Its flexible feeding habits and agile frame likely enabled it to exploit a range of food sources, small reptiles, insects, eggs, and even plant matter when opportunities arose. This ecological versatility may explain how sauropodomorphs first succeeded and spread across Pangaea before diverging into the colossal herbivores that would dominate Jurassic forests. In the grand saga of dinosaur evolution, Buriolestes represents a critical chapter, a moment when the lineage that would produce towering sauropods still wore the vestiges of its carnivorous origins. Its blend of primitive and derived traits offers a clear view of how early sauropodomorphs experimented with both form and function, balancing speed, agility, and feeding versatility. As new fossils emerge from the Triassic beds of Brazil and beyond, Buriolestes stands as a reminder that even the humblest of beasts can illuminate the grand tapestry of life on ancient Earth. Part 10. Eodromeus. Eodromeus murphy emerged from the ochre floodplain mudstones of Argentina's Esquigualesto Formation, dating to approximately 231 million years ago. Its fossils, unearthed in the mid-1990s but formally described in 2011, reveal one of the earliest known theropods, predating even well-known Jurassic carnivores by tens of millions of years. At barely 1.2 meters in length and weighing only around 10 kilograms, Eodromeus combined the lithe agility of small predators with anatomical clues foreshadowing later, larger saurischians. The preservation of nearly complete skeletons, including delicate skull bones and nearly intact limb girdles, provides an unparalleled window into the body plan and lifestyle of these pioneering dinosaurs. The depositional environment of the Esquigualesto Formation during the late Triassic consisted of meandering rivers, shallow lakes, and seasonal wetlands, all set against a backdrop of early conifer forests and fern thickets. Periodic volcanic ash falls blanketed living communities, preserving organisms in exquisite detail. Eodromeus shared this bustling ecosystem with primitive sauropodomorphs, armored atosaurs, and mammal-like synapsids. Such biodiversity fostered complex food webs, in which Eodromeus may have occupied a niche as a swift mesopredator, chasing down small vertebrates while avoiding larger Rhoesuchian predators that patrolled the same floodplains. The skull of Eodromeus exhibits a blend of primitive and derived features. The snout is elongated and ends with a slender premaxilla bearing 5 small, unserrated teeth, while the maxilla and dentary contain approximately 15 serrated teeth each. These recurved, laterally compressed teeth were adept at gripping slippery prey, such as early lizards or amphibians, and perhaps occasionally scavenging on soft plant matter. The lower jaw joint allowed a moderate gape, enabling it to swallow small items whole. Large orbits suggest good vision, likely enhancing its ability to detect movement in low-light conditions beneath the Triassic canopy. Limb proportions in Eodromeus point unequivocally to a specialist runner. The hind limbs are notably long, with a tibia exceeding the length of the femur, a characteristic shared with many fast-moving theropods. The metatarsals are slender and closely oppressed, forming a stiff foot ideal for rapid, repetitive strides. The ankle joint's hinge-like structure permitted a digitigrade posture, conserving energy over long distances. Strong muscle attachments on the pelvis and femur indicate robust hindquarter musculature, while a streamlined tail, stiffened by interlocking vertebral processes, acted as a dynamic counterbalance, stabilizing the body during quick maneuvers. Forelimb anatomy reveals three-fingered hands with sharp, hooked claws, each digit capable of grasping or raking motions. The delta pectoral crest on the humerus was well developed, suggesting powerful strokes that may have been used for grasping prey or aiding in balance during rapid turns. Although shorter than the hind limbs, the forearms retained a surprising degree of functional versatility. Some paleontologists propose that juveniles may have used their hands in climbing or probing for food, while adults relied predominantly on them for feeding behaviors, tearing flesh or manipulating vegetation. Histological examination of Eodromeus's bones reveals rapid juvenile growth, characterized by woven fibered bone tissue with extensive vascularization. This suggests a high metabolic rate, more akin to modern endotherms than to poikilothermic reptiles. The absence of pronounced lines of arrested growth indicates relatively constant growth rates with minimal seasonal slowdown. As individuals approached adult size, bone tissue transitioned to more organized lamellar structures, denoting a deceleration of growth. Such growth patterns would have enabled Eodromeus to quickly reach a size large enough to reduce predation risk, while still retaining the agility needed to hunt effectively. Eodromeus holds a pivotal place in dinosaur phylogeny, frequently recovered as a basal theropod. Its combination of ancestral Saurischean traits, such as a primitive hand structure, and derived features like advanced pelvic morphology, underscores the gradual acquisition of the theropod body plan. It illustrates how key adaptations for bipedal running, elevated metabolism and carnivory were already in place by the early Carnian stage. The clarity of its phylogenetic signal helps calibrate molecular and morphological clocks, anchoring the timing of major dinosaurian divergences at around 230 million years ago. Despite the wealth of skeletal data, Eodromeus retains mysteries. No direct evidence of integument, scales, proto-feathers, or a combination has been preserved, leaving its skin covering speculative. Its social behavior remains uncertain. While no mass mortality bone beds exist, trackways in similar aged formations hint at small group movement among early theropods. Reproductive strategies also elude researchers, as no nests or eggs have been definitively attributed to Eodromeus. Future discoveries in the Esquigualas strata or correlative deposits may yet uncover clues to these aspects of its biology. Eodromeus murphy stands as a testament to the Triassic dawn of theropods, combining speed, sensory acuity, and dietary versatility in a compact frame. As research continues, this unassuming predator will remain a focal point for unraveling the complex tapestry of early dinosaur evolution, illuminating how the first members of the lineage that would one day yield creatures as diverse as Tyrannosaurus and modern birds first ventured into terrestrial dominance. Part 11. Chromogisaurus. Chromogisaurus novasi roamed the late Triassic floodplains of northwestern Argentina. Roughly 231 million years ago, its slender form navigating a landscape dominated by braided rivers and ancient forests of ferns and early conifers. The genus name, meaning colored earth lizard, honors the vibrant red and purple hues of the soils in which its fossils were found. Measuring about 1.2 meters in length and weighing under 15 kilograms, Chromogisaurus represents one of the smallest and most basal members of Sauropodomorpha, the lineage that would later give rise to massive long-necked giants. Although diminutive, its anatomical features reveal a crucial stage in the evolution of herbivorous dinosaurs, bridging the gap between early omnivores and the colossal quadrupeds of later periods. The fossils of Chromogisaurus were unearthed in the upper levels of the Ischigualasto Formation, a geological treasure trove preserving the dawn of dinosaurian diversity. This formation captures sediment deposited by meandering streams and periodic volcanic ashfalls, creating fine-grained mudstones ideal for fossil preservation. Rapid burial under silt-laden floodwaters sealed the slender bones of Chromogisaurus, protecting delicate structures such as vertebral processes and phalanges. Its remains emerged alongside numerous contemporaries, offering a window into an ecosystem where early dinosaurs coexisted with pseudocekians, cynodonts, and early amphibians. The discovery history of Chromogisaurus highlights the collaborative nature of paleontology. In the early 2000s, a joint Argentine team led by Pablo Pol and Omar Alcoba excavated several partial skeletons from a remote stretch of the formation. Formal description followed in 2010, establishing Chromogisaurus novasi with a specific epithet honoring Argentine geologist Antonio Novas. Though the bones were scattered and incomplete, the sheer number of specimens spanning juveniles and adults enabled researchers to reconstruct much of its anatomy, from the pelvis to the forelimbs. Anatomical examination reveals a lightweight, agile dinosaur. Its hind limbs were notably elongated, with a tibia surpassing femur length, indicating a cursorial lifestyle. The foot bones, arranged in a slender three-toed configuration, ended in sharp claws ideal for rapid footfalls across muddy banks. The pelvis was streamlined, with a forward-pointing pubis that shifted the center of gravity close to the hips. This body plan facilitated swift bursts of speed and tight turns, adaptations useful for foraging among tight clusters of vegetation or evading larger predators. Skull material for Chromogisaurus is scarce, but the available jaw fragments and tooth impressions offer dietary clues. The teeth were small, leaf-shaped and serrated, suggesting a herbivorous diet focused on soft plant matter such as fern fronds and seedling shoots. Micro-wear patterns on tooth surfaces show fine striations consistent with shearing vegetation rather than gripping flesh. Nevertheless, the combination of sharp tooth edges and flexible jaw mechanics hints at occasional insect consumption or opportunistic scavenging, a dietary versatility that would have supported survival in fluctuating Triassic climates. The locomotive prowess of Chromogisaurus stands out among early sauropodomorphs. Its erect stance placed the torso well above the ground, while the stiffened tail acted as a dynamic counterweight. The robust muscle attachment sites on the femur and pelvis point to powerful leg muscles capable of sustaining prolonged movement. Trackway evidence from related Triassic sites supports stride lengths and pace consistent with an active forager covering extensive ground each day. Such mobility would have allowed Chromogisaurus to exploit dispersed resources across a mosaic of habitats. Phylogenetic analyses place Chromogisaurus near the base of Sauropodomorpha, just above even more primitive taxa like Saturnalia and Pampodromeus. Its mixture of ancestral traits, such as a relatively simple wrist joint, and derived features, like advanced pelvic morphology, marks it as a transitional form. The presence of early sauropodomorph characteristics in such a small-bodied species underscores how key adaptations for herbivory and quadrupedality began emerging incrementally long before the emergence of true sauropods in the Jurassic. Within its ecosystem, Chromogosaurus likely occupied a niche as a nimble herbivore, foraging on low vegetation while remaining alert to threats. Its small size and speed would have made it less vulnerable to the largest predators, yet it still faced competition and predation from early theropods and pseudo-Sissian archosaurs. The abundance of dental parallels with other basal sauropodomorphs suggests a shared feeding strategy, but Chromogosaurus's gracile limbs hint at a unique combination of browsing and swift evasion, a specialized lifestyle distinct from its larger, slower relatives. Many mysteries surround Chromogosaurus despite the wealth of postcranial remains. No direct evidence of skin coverings has been found, leaving its integument open to interpretation. Smooth scales, protofeathers, or a mosaic of both remain possibilities. Social behavior also remains speculative. Trackways of similar dinosaurs suggest potential group movement, but direct connections to Chromogosaurus are lacking. Continued excavations and advanced imaging techniques promise to uncover further details, but for now, Chromogosaurus stands as a testament to the inventive experimentation of early dinosaurs, a small pioneer whose evolutionary legacy echoes in the giants that followed. Part 12. Pisanosaurus. Pisanosaurus myrtiae lived during the late Triassic, around 228 to 216 million years ago, in what is now northwestern Argentina. Its bones were buried in the steam-fed floodplains of the Esquigualasto Formation, a place where rivers curved through fern thickets and volcanic ash occasionally blanketed the land. As one of the earliest dinosauriforms, or perhaps the oldest true ornithischian, Pisanosaurus stands at the threshold of dinosaur evolution. Measuring barely 1 meter from snout to tail tip and weighing under 15 kilograms, its small size belies the outsized role it plays in understanding how herbivorous dinosaurs first emerged from their carnivorous ancestors. The only known specimen of Pisanosaurus was discovered in 1962 by field teams mapping the Hoyada del Cerro Las Lajas locality. This single partial skeleton includes fragments of the lower jaw, several vertebrae, parts of the hip bones, complete hind limb elements, and scattered forelimb bones. The holotype's designation, PVL 2577, honors the paleontological collection at the Museo de Ciencias Naturales de San Juan. Early descriptions in the 1960s recognized its unique combination of features, but only with advances in comparative anatomy and modern phylogenetic methods did its importance as a potential basal ornithischian become clear. Skeletal anatomy reveals a lightweight, bipedal frame optimized for both speed and balance. The hind limbs feature a tibia slightly longer than the femur, and the elongated metatarsals form a slender three-toed foot built for quick, repetitive strides. The pelvis displays a backward-oriented pubis, a defining trait of ornithischians, yet some aspects of its hip and ankle bones remain primitive, echoing its transitional status. The long tail, stiffened by overlapping vertebral processes, would have functioned as a dynamic counterbalance, stabilizing the body during rapid directional changes across floodplain mud and shifting gravel bars. Jaw anatomy offers clues to diet and feeding behavior. The lower jaw bears a series of small leaf-shaped teeth with fine serrations, ideal for shearing soft plant tissues. Premaxillary teeth near the front appear more conical, hinting at occasional insectivory or opportunistic consumption of small invertebrates. Microscopic wear patterns on the tooth surfaces reveal both slicing and grinding motions, suggesting brushing foliage and perhaps cropping low, growing ferns or horsetails. This mixed feeding strategy would have provided valuable dietary flexibility in an environment where seasonal floods and ashfall events could abruptly alter food availability. Forelimb elements, though fragmentary, indicate capable grasping functions. The scapular and humerus fragments show robust muscle attachment sites, while the partial metacarpals and phalanges hint at slender fingers tipped with modest claws. These forelimbs may have been used for stabilizing against low vegetation or assisting in food manipulation. Such manual dexterity, combined with a bipedal stance, paints Pisanosaurus as a creature that could forage with both limbs, reaching into dense undergrowth for tender shoots and repositioning food items for more efficient processing. The precise phylogenetic position of Pisanosaurus remains a subject of active debate. Many researchers place it as the oldest known ornithischian dinosaur, the bird-hipped lineage that would later include stegosaurs and ceratopsians. Others argue it belongs just outside Dinosauria, among the silosaurids, close cousins of true dinosaurs. Shared features such as the pubic orientation and tooth morphology support an ornithischian identity, while certain primitive hip and ankle traits invite caution. Resolving this debate carries major implications for the timing and pattern of early dinosaur diversification. The Ischiguala's ecosystem was a tapestry of Triassic life. Armored atosaurs grazed alongside rhynchosaurs, early theropods like Herrerasaurus prowled, and cynodonts scurried through underbrush. Seasonal rivers carved channels that left sandy banks and silted floodplains. Subtropical temperatures and monsoonal rains fostered rapid plant growth, while periodic volcanic eruptions blanketed the landscape with ash, preserving bone beds that reveal intricate community structures. In this dynamic setting, Pisanosaurus occupied a niche as a small herbivore-omnivore, nipping foliage where competition from larger herbivores was minimal. Bone histology of related early ornithischians indicates rapid juvenile growth and elevated metabolic rates, traits Pisanosaurus likely shared. Its limb bones, though too fragmentary for detailed histology, would have grown quickly to reach a vulnerable escaping size before seasonal predators struck. Continuous bone deposition patterns, if confirmed, would align Pisanosaurus with an active endotherm-like physiology, enabling sustained foraging and swift flight from danger, much like modern birds and mammals. Despite its pivotal role, Pisanosaurus leaves many mysteries. No skin or scale impressions have been recovered, leaving its integument, scales, proto-feathers or a mosaic an open question. Nesting behavior, social structures and precise growth curves await discovery of additional specimens. Each new find in the Triassic deposits of Argentina offers hope for unveiling these secrets. For now, Pisanosaurus myrtiae remains a tantalizing glimpse of the first steps taken by the ornithischians, pioneers whose lineage would one day produce armored, plated, and horned dinosaurs that dominated Mesozoic landscapes. Part 13. The Codontosaurus. The Codontosaurus antiquus roamed the damp floodplain forests of southwestern England during the Rhaetian stage of the late Triassic, roughly 205 million years ago. Its remains were preserved in limestone fissures near Bristol, where acidic water had dissolved ancient bedrock to create pockets that trapped bones washed in by seasonal floods. Measuring about 2 meters long and standing less than a meter tall at the hip, the Codontosaurus combined a small, lightweight body with surprisingly robust legs. Its stature allowed it to weave through dense understory plants and quickly escape larger predators that shared its world. Its discovery in the 1830s placed the Codontosaurus among the first dinosaurs recognized by science, predating even many more famous genera. Quarry workers uncovered its teeth and jaw fragments, leading naturalists to realize they had found a reptile unlike any other. Early descriptions in the mid-19th century established its unique tooth sockets and bony crest above each eye, features that distinguished it from crocodilian and amphibian fossils common in the same deposits. As paleontology matured, the Codontosaurus emerged as a key specimen for understanding dinosaur origins in Europe. Skull fragments reveal a short, triangular head with a stout lower jaw lined by leaf-shaped teeth. These serrated chisel-like teeth suggest a herbivorous diet focused on low-growing vegetation such as ferns and horsetails. Wear patterns on the teeth show fine striations consistent with slicing through tough plant fibers, while occasional pits imply ingestion of small seeds or insects. The broad beak-like front of the jaw would have helped the animal nip tender shoots. Combined, these dental features paint a picture of a versatile browser that adapted to the changing Triassic flora. The vertebral column of the Codontosaurus exhibits both rigidity and flexibility. The tall neural spines on its back vertebrae anchored powerful muscles that held its torso aloft, while the gradually tapering tail vertebrae formed a whip-like counterweight for balance during rapid movements. Fusion of sacral vertebrae to the pelvis created a stable base for the hind limbs, enabling efficient stride cycles. These adaptations allowed the Codontosaurus to shift between grazing and swift locomotion, darting across open patches between fern thickets when threatened by carnivores. Limbs of the Codontosaurus reveal a bipedal posture with occasional quadrupedal forays. The hind legs featured elongated femurs and tibias, indicating cursorial specialization for speed, while the shorter arms, ending in five-fingered hands, suggest they were used for grasping vegetation or stabilizing the body during slower feeding. Claw-tipped digits may have helped in manipulating branches or digging for roots. This combination of limb proportions reflects an evolutionary experiment in body plan that balanced feeding efficiency with predator avoidance. Paleo-environmental reconstructions depict a warm, humid landscape with cyclical monsoonal rains and river channels that meandered across broad floodplains. Volcanic ash layers occasionally blanketed the region, preserving entire animal communities in fine detail. The Codontosaurus shared its habitat with armored atosaurs, early crocodile relatives, and mammal-like cynodonts, creating a rich tapestry of Triassic life. Its presence in multiple fissure sites indicates it was a successful and widespread herbivore within this complex ecosystem. Bone histology of related Triassic dinosaurs suggests rapid juvenile growth with high metabolic rates, and the Codontosaurus likely followed a similar pattern. Its limb bones show dense vascular canals for fast bone deposition, indicating individuals reached adult size within a few years. This accelerated growth would have reduced juvenile vulnerability to predators, allowing for early independence. As growth slowed in maturity, bone tissue transitioned to more organized lamellar structures, reflecting a shift in energy allocation toward maintenance rather than rapid size gain. Phylogenetically, the Codontosaurus occupies a basal position among sauropodomorph dinosaurs, bridging the gap between early bipedal forms and the later giants that would roam Jurassic plains. Its mix of primitive traits, such as five-fingered hands, and more derived characteristics, like herbivorous teeth and cursorial legs, highlights the gradual assembly of the sauropodomorph body plan. This mosaic anatomy underscores the stepwise evolutionary process by which small, agile Triassic herbivores gave rise to the colossal, long-necked sauropods. Despite its early discovery and study, the Dinosaurus still harbors mysteries. No soft tissue impressions have confirmed its skin covering, leaving conjecture between scales or simple filamentous structures. Social behavior and reproductive strategies remain speculative, though trace fossils of similarly sized dinosaurs suggest possible group movements. Continued excavation of fissure deposits and advances in imaging techniques hold promise for unraveling these enigmas, ensuring that the Dinosaurus remains a focal point in the unfolding story of dinosaur origins. Part 14. Plateosaurus. Plateosaurus trosingensis dominated the temperate floodplains of Central Europe during the Norean stage of the late Triassic, roughly 210 to 204 million years ago. As one of the earliest and most abundant sauropodomorph dinosaurs, Plateosaurus marks the beginning of an evolutionary line that would eventually lead to the gigantic, long-necked sauropods of the Jurassic. Its fossils first emerged from the red beds of the Trossingen Formation near Stuttgart, Germany, revealing an animal that combined modest size in its youth with the potential for extraordinary growth. This duality between small, agile juveniles and vast, ponderous adults underscores the remarkable developmental plasticity of Plateosaurus, a trait that set the stage for sauropod gigantism. The story of Plateosaurus's discovery stretches back to the early 1830s, when quarry workers in Trossingen uncovered curious jaw fragments and teeth, unlike those of crocodiles or amphibians. Academic interest peaked when Hermann von Meyer formally named the genus in 1837, making Plateosaurus one of the first dinosaur genera ever identified. For decades, its classification wavered as naturalists debated whether it was a reptile, a bird ancestor, or something altogether new. It wasn't until the late 19th and early 20th centuries that paleontologists recognized its Saurischian affinities, cementing Plateosaurus's status as a cornerstone in the burgeoning field of dinosaur research. Extraordinary numbers of Plateosaurus skeletons, over 100 individuals, have been excavated from sites across Germany, Switzerland, and France. These mass death assemblages suggest periodic flooding events that swept herds of animals into low-lying depressions, burying them rapidly under sediment. Such bone beds provide a rare glimpse into herd dynamics, hinting that Plateosaurus lived and perhaps migrated in groups. The sheer volume of remains, ranging from tiny juveniles to massive adults, offers unparalleled insight into the life history and growth patterns of a single dinosaur species across decades and varying environmental conditions. Skull material, though relatively small compared to body size, reveals a head designed for efficient plant processing. A long, flexible neck allowed grazing at various heights, while the lower jaw housed dozens of leaf-shaped, serrated teeth, specialized for slicing soft vegetation. Micro-wear patterns on these teeth indicate both slicing motions and occasional grinding, suggesting that Plateosaurus's diet may have included tougher plant parts or even opportunistic insect consumption. The combination of a small skull, broad muzzle, and precise jaw mechanics provided a feeding apparatus capable of exploiting diverse Triassic flora with ease. Locomotor anatomy firmly establishes Plateosaurus as an obligate biped. Early theories posited quadrupedal gaits based on sprawling reconstructions, but careful study of the forelimb bones revealed an inability to pronate the hands. Rotation of the palms to the ground was impossible. Coupled with the forelimb's shorter length relative to robust hind limbs and a center of mass positioned over the hips, it became clear that Plateosaurus walked and ran on two legs. Digigrade posture, standing on the toes, further enhanced stride length and speed, allowing this dinosaur to traverse floodplain environments quickly when foraging or evading threats. One of the most striking aspects of Plesiosaurus biology is its developmental plasticity. Bone histology shows rapid, woven-fibered bone deposition in juveniles, enabling them to reach lengths of 5 to 6 meters within a decade. As individuals matured, growth rates diverged dramatically. Some plateaued at under 5 meters, while others continued growing to nearly 10 meters long and tipping the scales at several tons. This variability, rare among vertebrates, suggests that environmental factors such as food availability and climate played a significant role in determining adult size. Plesiosaurus thus offers a window into how early dinosaurs could modulate growth in response to ecological pressures. Biomechanical studies of Plesiosaurus vertebrae and limb bone cross-sections reveal an animal built for both endurance and rapid bursts of speed. Its erect hind limb posture and elongated lower leg segments facilitated efficient locomotion, while sturdy muscle attachments on the pelvic girdle and femur indicate powerful strides. The tail, rigidened by interlocking vertebral processes, served as an effective counterbalance. Modeling of gait dynamics suggests that Plesiosaurus could vary its stride frequency to achieve different speeds, relying on rapid leg retraction rather than energy-intensive aerial phases typical of running mammals. Paleoecological evidence paints Plesiosaurus's world as one of seasonal extremes. Floodplain channels shifted with monsoonal rains, creating a patchwork of wetlands and dry uplands. Conifer forests and fern thickets provided abundant forage, while occasional droughts and ash falls from nearby volcanic activity altered habitats dramatically. In this shifting landscape, herd behavior would have offered protection against theropod predators, and plastic growth strategies allowed Plesiosaurus to capitalize on both lean and flush resource years. Their footprints, found in parallel trackways, testify to group movements across muddy flats, reinforcing the image of a social dinosaur navigating a changeable world. Despite decades of intensive study, questions about Plesiosaurus endure. No direct evidence of integument, scales, or proteo feathers has been preserved, leaving its skin covering a matter for speculation. Nesting sites remain elusive, though the diversity in juvenile sizes hints at communal breeding grounds. As paleontologists continue to unearth new specimens and apply innovative imaging and geochemical techniques, Plesiosaurus remains a vital key to understanding how modest beginnings blossomed into the greatest terrestrial giants the world has ever seen. Part 15. Coelophysis. Coelophysis bari prowled the sun-baked floodplains of what is now the American Southwest, approximately 203 million years ago, during the Norean stage of the late Triassic. Its fossils, uncovered in astonishing numbers at Ghost Ranch, New Mexico, tell of a creature both slender and fierce, measuring up to 3 meters in length, yet tipping the scales at a mere 15 to 20 kilograms. These long-legged, hollow-boned dinosaurs form the earliest well-documented theropod lineage, foreshadowing the rise of giants like Tyrannosaurus and the flight-capable raptors of the Cretaceous. The discovery of mass death assemblages, a tapestry of dozens of entwined skeletons, painted a vivid picture of sudden flood events that claimed entire groups, preserving Coelophysis in lifelike poses for science to unravel centuries later. The skull of Coelophysis was exquisitely lightweight, with large eye orbits revealing a keen vision, suited for hunting in dappled floodplain forests. Its slender snout housed dozens of recurved, serrated teeth, each designed to pierce and slice through flesh. Unlike later tyrannosaurs with bone-crushing jaws, Coelophysis' bite was optimized for gripping small prey, lizards, early mammals, and even its own hatchlings, as skeletal evidence suggests. Occasional cannibalism under harsh conditions. A flexible lower jaw allowed a generous gape, capturing swift-moving victims and swallowing them in rapid succession. This combination of speed and precision made Coelophysis a deadly predator among the earliest dinosaurs. Limb anatomy highlights Coelophysis' mastery of speed and agility. Its hind limbs were long and gracile, featuring a tibia longer than the femur, a hallmark of rapid runners. Digigrade feet ended in sharp claws, offering traction on muddy banks and rocky creek beds. The pelvis and hips bore strong muscle scars indicative of powerful thigh musculature, propelling the animal in bursts of up to 40 kilometers per hour. The stiffened tail, reinforced by overlapping vertebral processes, served as a dynamic counterbalance during high-speed turns. Such adaptations allowed Coelophysis to chase prey across open flats or weave through dense vegetation with remarkable ease. Forelimbs, though shorter than the hind legs, retained considerable functionality. Three-fingered hands bore slender, recurved claws, capable of grasping struggling prey or clinging to vegetation. Muscle attachment sites on the humerus and shoulder girdle indicate enough strength for deliberate manipulations, perhaps opening carcasses or pulling down small branches. These versatile hands hint at a multi-purpose role, blending predatory strikes with foraging behaviors when larger prey was scarce. This adaptability underscores how early theropods experimented beyond pure pursuit predation, exploiting varied food sources in Triassic ecosystems. The vision and sensory adaptations of Coelophysis further enhanced its hunting prowess. Large, forward-facing eyes provided overlapping fields of view, enabling depth perception crucial for judging distances during high-speed pursuit. Internal casts of the brain case reveal an expanded flocculus in the cerebellum, suggesting excellent balance and head stability while running. Olfactory bulbs, though not as pronounced as in later tyrannosaurs, indicate a decent sense of smell, useful for tracking prey or locating carrion. Together, these senses crafted a predator finely tuned to its environment, capable of both stealth and sudden bursts of activity. Growth studies using bone histology show that Coelophysis grew rapidly, attaining adult dimensions within just a few years. Woven fibered bone tissue with abundant vascular canals characterizes juvenile specimens, pointing to high metabolic rates and elevated activity levels. As individuals matured, bone deposition shifted toward more organized lamellar structures, marking a slowdown in growth once reproductive maturity was reached. This growth trajectory mirrors strategies seen in modern birds and mammals, supporting the view that dinosaurs had active, endotherm-like physiologies far earlier than once believed. Paleoecological reconstructions position Coelophysis within a mosaic of late Triassic life. Seasonal rains fed braided rivers and ephemeral lakes, while monsoon-like rains transformed arid flats into lush feeding grounds. Coelophysis shared these floodplains with early sauropodomorphs, armored etosaurs, and mammal ancestors called cynodonts. Volcanic eruptions periodically blanketed the region in ash, triggering mass mortality events reflected in bone beds. Within this dynamic tapestry, Coelophysis thrived as both predator and scavenger, its small size allowing access to niches unreachable by larger carnivores. Despite its fame, many aspects of Coelophysis remain enigmatic. Debate continues over the extent of social behavior. Mass death sites suggest herd movements, yet taxonomic biases could exaggerate group associations. No direct skin impressions have been found, leaving conjecture between scaly hide or simple filamentous coverings. Nesting sites are unknown, though some scientists propose communal nests based on comparisons with related theropods. Each new excavation in the southwestern deserts brings hope that these mysteries may one day be resolved, shedding fresh light on the life of one of Earth's earliest agile predators. Coelophysis bari stands as an icon of early dinosaur evolution, a creature that captured the imagination of scientists with its speed, versatility, and resilience. From its fossilized remains entombed under floodwaters to its role as a pioneer of the theropod lineage, Coelophysis weaves a story of adaptation and survival at the dawn of the age of dinosaurs. Every bone fragment, every claw impression, and every mass assembly underscores the complexity of Triassic ecosystems and the evolutionary innovations that would shape the Mesozoic world for the next 160 million years. Part 16. Liliensternus. Liliensterni stalked the steamy woodlands of late Triassic Germany roughly 205 million years ago, its sleek form gliding between towering primitive conifers and tree ferns. First recognized in 1934 from partial skeletons unearthed near the town of Halberstadt by Friedrich von Huene, this medium-sized theropod measured up to 6 meters in length and weighed close to 200 kilograms. Its lightweight bones bore hollow chambers, reducing weight without sacrificing strength, an early innovation that allowed Liliensternus to balance speed with endurance. Long, narrow legs propelled it across floodplain flats, while a rigid tail served as a dynamic counterweight, stabilizing rapid turns as it pursued small herbivorous dinosaurs and early mammal relatives. The quarry sites where Liliensternus fossils emerged are testament to the rich biodiversity of the Trossingen Formation. Alongside its bones lay remains of Plateosaurus herds, armored atosaurs, and early ranchosaurs, all buried in a fine matrix of silt and volcanic ash after sudden flooding events. These mass mortality assemblages preserve multiple growth stages, from juvenile to adult, providing a unique window into life history. Examination of articulated limb elements and vertebral columns shows that Liliensternus skeletons were often complete when buried, suggesting rapid sedimentation that entombed these predators in situ during seasonal overbank flows. The skull of Liliensternus was a marvel of predatory design. A long, narrow snout held sharp, laterally compressed teeth serrated on both edges, ideal for slicing through flesh and tendon. The antorbital fenestra, a large opening before the eye socket, lightened the skull while accommodating powerful jaw muscles. Its lower jaw could swing wide, enabling large bites into struggling prey, and the palate bore recessed surfaces that strengthened the skull against torsion. These cranial features positioned Liliensternus as an efficient mesocarnivore, capable of subduing nimble prey without sacrificing bite force. Musculoskeletal adaptations underscore Liliensternus's prowess as a runner. The hind limbs feature a femur and tibia of nearly equal length, with an elongated metatarsus, an arrangement optimizing both stride and propulsion. The knee joint permitted a spring-like action, storing and releasing energy with each step, while the ankle's hinge allowed precise foot placement on uneven ground. Footprint tracks matched to Liliensternus dimensions reveal stride lengths of over 2 meters, suggesting peak speeds surpassing 35 kilometers per hour. In the shifting mosaic of floodplains and woodlands, such agility would have been crucial for both hunting and evading larger predators. Forelimbs of Liliensternus, though shorter than its legs, played a critical role in prey capture. Each hand bore 3 fingers tipped with curved razor-sharp claws. Robust muscle attachment scars on the humerus and ulna indicate substantial forearm strength, allowing Liliensternus to grasp and hold struggling prey while delivering killing bites. The shoulder joint permitted a wide range of motion, enabling sweeping slashes or secure grips. This dual functionality, speedy pursuit combined with manual dexterity, reflects an evolutionary experimentation among early theropods, blending pursuit predation with grappling feeding strategies. Paleoecological studies of the Trossingen beds reveal a subtropical climate with pronounced wet and dry seasons. Braided rivers coursed through open woodlands where cycads and horsetails thrived. Volcanic ash from distant eruptions occasionally smothered the land, preserving snapshots of animal life suddenly buried. In this dynamic environment, Liliensternus likely exploited both open floodplain areas to chase prey and denser vegetation for ambush hunting. Bonebed taphonomy suggests that groups of Liliensternus may have hunted or scavenged together, taking advantage of mass death events to claim easy meals from flood-stranded carcasses. Growth patterns gleaned from bone histology indicate rapid early development in Liliensternus. Juvenile limb bones show thick deposits of woven fibered bone and extensive vascular networks, signifying accelerated growth rates and elevated metabolism. As individuals matured, bone tissue organization shifted toward lamella-zonal bone, marking a slowdown in growth once adult size was reached. This ontogenetic trajectory parallels that of many later dinosaurs and modern birds, suggesting an early establishment of endotherm-like physiology within theropoda, supporting sustained activity and quick recovery from exertion. Phylogenetically, Liliensternus occupies a pivotal position within Neotheropoda, a clade that gave rise to both ceratosaurs and tetaneurons, the latter including such Jurassic luminaries as Allosaurus and the birdline theropods. Its blend of primitive traits, like a relatively unspecialized pelvis, and derived characters, such as elongate metatarsals, illuminates the gradual assembly of the theropod body plan. Comparative analysis with coeval genera like Dilophosaurus from North America underscores convergent evolutionary trends in skull fenestration and limb design, hinting at parallel adaptations to predatory lifestyles across Pangaea's breakup. Despite extensive study, mysteries linger around Liliensternus. No direct integumentary evidence, scales or proto-feathers has been preserved, leaving its skin coverings an open question. Social structure and reproductive behavior remain speculative, while mass assemblages imply group dynamics. Alternative taphonomic processes could also concentrate carcasses. Ongoing excavations and technological advances in imaging and geochemistry promise to unveil further secrets. For now, Liliensternus stands as a testament to the inventive experimentation of early carnivorous dinosaurs, bridging the evolutionary gulf between primitive Triassic predators and the mighty hunters of the Jurassic and Cretaceous. Part 17. Dracovenata. In the early Jurassic period, around 201 to 199 million years ago, a formidable predator roamed the floodplains of what is now South Africa. This dinosaur, known as Dracovenata regenti, meaning dragon hunter, was a bipedal carnivore that played a significant role in its ecosystem. The name reflects its discovery near the Drakensberg Mountains, whose name translates to Dragon's Mountain. The species name honors Regent Lucas Hoomer, a field assistant who co-discovered the fossils alongside paleontologist James Kitching. The holotype specimen, BP1 5243, includes partial cranial elements such as both premaxillae, fragments of the maxillae and dentary, parts of the cerangular, angular, prearticular, and articular bones, as well as several teeth. These remains provide valuable insights into the anatomy and evolutionary relationships of early theropods. Dracovinator was a medium-sized, moderately built, ground-dwelling, bipedal carnivore, estimated to measure between 5.5 and 6.5 meters in length and weigh around 400 kilograms. Its build suggests a combination of agility and strength, allowing it to be an effective predator. The partial skull remains reveal a kink between the premaxillae and maxilla bones, a feature reminiscent of its relative Dilophosaurus. This cranial morphology indicates adaptations for a powerful bite, suitable for subduing prey in its ecosystem. The presence of serrated teeth and robust jaw bones further supports its classification as a carnivorous theropod. The paleo-environment of the Upper Elliott Formation, where Dracovinator was discovered, was characterized by fluvial floodplains with a diverse assemblage of flora and fauna. This habitat supported various herbivorous dinosaurs, such as Massospondylus, which likely served as prey for predators like Dracovinator. The presence of multiple dinosaur taxa in this formation underscores the ecological complexity of early Jurassic ecosystems in southern Africa. Fossils of ornithischian dinosaurs, including Abrictosaurus, Fabrosaurus, Heterodontosaurus, and Lesothosaurus, have also been recovered from the Upper Elliott Formation, highlighting the rich biodiversity of the region during this period. Phylogenetic analyses placed Dracovinator within the Neotheropoda clade, closely related to genera like Dilophosaurus and Zoopasaurus. This positioning highlights the diversity and widespread distribution of early theropods during the early Jurassic period. The combination of primitive and derived features in Dracovinator's anatomy contributes to our understanding of theropod evolution and the emergence of later, more specialized carnivorous dinosaurs. The skull of the type specimen exhibits a mosaic of both ancestral and derived theropod characteristics, providing valuable insights into the evolutionary transitions within this group. Though despite the fragmentary nature of the fossil record for Dracovinator, the available material provides valuable information about its feeding adaptations. The serrated teeth and robust jaw bones suggest a diet consisting of vertebrate prey, consistent with its classification as a carnivorous theropod. The morphological features observed in the cranial elements indicate a capacity for delivering strong bites, essential for capturing and processing prey. These adaptations would have been advantageous in the diverse and competitive ecosystems of the early Jurassic. The severity of Dracovinator contributes to the broader understanding of theropod diversity during the early Jurassic, particularly in Gondwanan continents like Africa. Its close relationship with other early theropods from different regions highlights the widespread distribution and evolutionary experimentation occurring among predatory dinosaurs during this time. These findings emphasize the importance of southern Africa in the study of dinosaur evolution and the need for continued paleontological research in the region. Ongoing research and exploration in the Elliott Formation and other early Jurassic sites continue to shed light on the diversity and adaptations of early dinosaurs. Each new discovery, including that of Dracovinator, adds to the intricate mosaic of life's history, illustrating the dynamic processes that have shaped the evolution of terrestrial vertebrates over millions of years. The continued study of these fossils provides valuable insights into the evolutionary pathways that led to the dominance of dinosaurs in the Mesozoic era. The show Dracovinator regenti stands as a testament to the rich paleontological heritage of South Africa and the critical role of collaborative fieldwork in uncovering the secrets of ancient life. Its discovery not only enhances our understanding of theropod evolution, but also underscores the significance of preserving and studying fossil records to unravel the complex narrative of Earth's biological past. The contributions of dedicated researchers and field assistants, such as Regent Lucas Huma, highlight the collaborative nature of paleontological discoveries and the importance of recognizing the efforts of all individuals involved in these endeavors. So, in summary, Drecovenator regenti provides a valuable glimpse into the early evolution of theropod dinosaurs in the early Jurassic of southern Africa. Its anatomical features, ecological context, and phylogenetic relationships contribute to a deeper understanding of the diversity and adaptations of early carnivorous dinosaurs. As ongoing research continues to uncover new information about this fascinating genus, Drecovenator remains an important subject of study in the field of paleontology. Part 18. Massospondylus. Massospondylus carinatus roamed the floodplains and river valleys of southern Africa during the early Jurassic, around 200 million years ago, as one of the first prosauropods, and among the most common dinosaurs in its environment. It offers a window into the transition from small, bipedal herbivores to the gigantic long-necked sauropods that would dominate later eras. Known from dozens of nearly complete skeletons, Massospondylus has become emblematic of early dinosaur life. Its remains preserved in mudstone and sandstone layers of the Elliott Formation. These fossils reveal a creature built for both browsing on low vegetation and swift locomotion across open landscapes. First described in the mid-19th century, Massospondylus was among the earliest dinosaurs ever recognized by science. Initial finds in 1853 surfaced near the farm Gardveld in South Africa's Free State province, and the genus name, meaning long vertebra, alludes to the elongated neck bones that distinguished it from its contemporaries. Early paleontologists puzzled over its anatomy, debating whether it walked on 2 legs or 4. Only with the discovery of juvenile skeletons in the 1990s did researchers confirm a primarily bipedal stance, with occasional use of the forelimbs for foraging, reinforcing its role as a nimble, adaptable herbivore. Anatomical studies reveal a small, delicate skull perched atop a graceful, S-shaped neck, composed of at least 13 elongated cervical vertebrae. Its jaws were lined with spatulate, serrated teeth perfectly suited for stripping leaves from ferns, horsetails and cycads. Microscopic wear patterns on these teeth indicate both slicing and grinding motions, suggesting a mixed feeding strategy that could include tougher plant material when needed. The combination of neck length and dental specialization allowed Massospondylus to exploit a broad swath of vegetation without expending energy uprooting plants. Limbs of Massospondylus exhibit a clear bipedal bias, with hind limbs that were long, straight and powerful. The femur and tibia reached nearly equal lengths, promoting efficient, spring-like strides, while the pelvis provided robust muscle attachments for sustained locomotion. Forelimbs, though shorter, were no afterthought. Each hand bore 5 digits, the first of which carried an enlarged thumb-like claw. This claw may have helped in grasping low-lying branches or digging for tubers, indicating a degree of manual dexterity that enriched its feeding repertoire. The paleo-environment of the Elliott Formation was a mosaic of braided rivers, seasonal lakes and wetlands fringed by conifer groves and fern thickets. Volcanic ash falls periodically blanketed the region, preserving entire herds of Massospondylus in mudflows that entombed juveniles and adults alike. These sites, some containing dozens of individuals, hint at possible herding behavior or at least seasonal congregations at river crossings. The rich faunal assemblage, rhynchosaurs, early crocodile relatives, and carnivorous theropods paints a picture of a complex ecosystem in which Massospondylus thrived as a primary consumer. Insights into the reproductive biology of Massospondylus come from remarkable egg and embryo discoveries in China's Upper Shaximia Formation, where embryos within leathery eggs closely match its skull anatomy. These finds suggest that mass nesting may have occurred, possibly in communal colonies. Embryonic bone histology shows rapid development of limb bones even before hatching, indicating precocial young capable of moving soon after emergence. Such early maturity would have been vital for evading predators in a world where larger carnivores prowled the same floodplains. Growth studies of Massospondylus limb bones reveal an initial phase of rapid, nearly uninterrupted growth, followed by a slowdown as individuals reach skeletal maturity. Juveniles appear to have grown to half-adult size within a few years, then continued a steadier increase over a decade or more. This two-phase growth strategy parallels that of modern mammals and birds, supporting the notion that early dinosaurs possessed elevated metabolic rates. Such physiology would have fueled the active lifestyles inferred from their agile bodies and wide geographic distribution. Debate surrounds the locomotor shift in Massospondylus's life history. Some evidence suggests juveniles were strictly bipedal, while larger adults may have become facultatively quadrupedal, using their forelimbs for additional support as body mass increased. This ontogenetic shift foreshadows the full quadrupedality of later sauropods and underscores how early prosauropods were experimenting with limb functions and posture. Tracking these changes in bone robusticity and joint morphology helps unravel the steps that led to the colossal giants of the Jurassic. In its blend of slender grace and sturdy adaptability, Massospondylus carinatus stands as a pivotal experiment in dinosaur evolution. From its elongated neck and versatile jaw to its swift limbs and communal nesting, it exemplified the innovations that would propel sauropodomorphs into monumental success. Each new discovery, be it a juvenile skeleton, an embryo-filled nest, or a revised growth curve, adds depth to the portrait of a dinosaur that bridged the gap between the nimble pioneers of the late Triassic and the towering titans of the Mesozoic. Part 19. Zoopesaurus. Zoopesaurus rosieri prowled the floodplains of northwestern Argentina during the late Triassic, roughly 213 million years ago. Its fossilized remains, recovered from the Los Colorados Formation near Villa Union, reveal a predator that combined slender agility with surprising cranial ornamentation. Measuring approximately 4 meters in length and weighing close to 150 kilograms, Zoopesaurus was one of the earliest known theropods in South America. Its long gracile limbs supported a gait primed for speed and maneuverability across muddy riverbanks and fern-covered marsh edges. Despite its moderate size, the animal's skull tells a story of fierce competition. Two parallel ridges above its eye sockets hint at primitive crest structures, foreshadowing the extravagant headgear of later dinosaurs. The skull of Zoopesaurus is perhaps its most intriguing feature. The paired ridges, one above each orbit, may have served as display structures, drawing the attention of potential mates or warning rivals. Each ridge was formed by pronounced nasal bones, fused and elongated to create a striking V-shaped crest. Although no direct evidence reveals coloration or soft tissue frills, these bony prominences suggest the early experimentation with visual signaling among theropods. Below these crests lay a narrow snout lined with serrated, blade-like teeth, each recurved to prevent prey escape. The combination of display and deadly dentition made Zoopesaurus both an object of fascination and a formidable hunter in its ecosystem. Limb anatomy underscores Zoopesaurus's role as an active pursuer. Its hind limbs were long and slender, characterized by a tibia slightly longer than the femur, a hallmark of animals built for rapid running. The metatarsals and phalanges formed a compact foot with strong clawed toes, enabling secure traction on slippery or uneven terrain. The pelvis displayed well-developed muscle attachment areas, hinting at powerful thigh musculature that could launch the dinosaur into sudden bursts of acceleration. Agile turns were facilitated by a stiffened tail, whose vertebrae were reinforced by elongated processes that resisted lateral bending while running. Together, these features paint a picture of a swift carnivore capable of chasing down small reptiles, amphibians, and even young prosauropods. Forelimbs of Zoopisaurus, while shorter than its hind legs, were far from vestigial. Each arm bore 3 fingers tipped with recurved claws, and muscle scars on the humerus reveal considerable forearm strength. These forelimbs likely served multiple functions, grasping struggling prey during the final stages of a hunt, manipulating objects such as fallen logs to uncover hidden invertebrates, and perhaps aiding balance during rapid turns. Such dexterity illustrates the evolutionary experimentation among early theropods, blending pursuit predation with occasional foraging behaviors. Zoopisaurus thus embodied a versatile approach to resource acquisition, able to switch between active hunting and opportunistic scavenging. The paleo environment of the Los Colorados Formation was a tapestry of river channels, seasonal lakes and vegetated floodplains dominated by seed ferns, horsetails, and early conifer relatives. Volcanic activity in the region periodically blanketed the landscape with ash, creating sudden death assemblages that preserved not only Zoopisaurus skeletons, but also footprints and plant imprints. These mudflows and lahars entombed entire communities, offering paleontologists a frozen tableau of Triassic life. In this shifting world, Zoopisaurus likely followed floodplain corridors in search of both prey and nesting sites, its migratory patterns driven by seasonal rains and the ebb and flow of water sources. Growth patterns inferred from bone morphology suggest Zoopisaurus experienced a rapid juvenile phase, characterized by thin cortical bone and porous internal structure, followed by a slower maturation period. While direct histological sampling of its bones remains limited, comparisons with related theropods indicate that it likely attained nearly adult size within 3 to 4 years. This accelerated growth would have reduced juvenile vulnerability to larger predators and allowed earlier entry into reproductive cycles. Once adult proportions were reached, growth slowed, directing energy toward maintenance rather than further increases in size. Ecological interactions with contemporary dinosaurs shed light on Zoopisaurus's place in the food web. Coexisting carnivores, such as the larger Herrerasaurus and the smaller, agile Coelophysis, occupied overlapping territories, likely partitioning prey based on size and hunting strategy. Zoopisaurus, with its intermediate size and mixed hunting tactics, may have specialized in mid-sized prey, juvenile herbivores and smaller synapsids, filling a niche between the lightning-fast pursuit of smaller theropods and the brute force of larger predators. Such niche differentiation would have reduced direct competition and contributed to the high diversity of carnivorous dinosaurs in the late Triassic. Phylogenetic analyses place Zoopisaurus near the base of the Ceratosauria, or in a closely allied neotheropod grade, highlighting its value for understanding early theropod diversification. Its blend of primitive features, such as the retention of 5 digits on each hand and derived traits like cranial crests and hollow limb bones, illustrates the mosaic nature of dinosaur evolution. By studying Zoopisaurus, Paleontologists gain insights into how display structures and locomotive adaptations emerged in parallel, setting the stage for the later evolution of iconic crested theropods and the incredible diversity of predatory dinosaurs that followed. The discovery of Zoopasaurus rougier enriches the narrative of Triassic dinosaur evolution by revealing both the physical adaptations and ecological strategies that enabled early theropods to thrive. From its dramatic cranial ridges to its powerful limbs and agile hunting style, Zoopasaurus demonstrates that the roots of dinosaurian success lay in a combination of speed, strength, and social signaling. As new specimens continue to emerge from the rocky outcrops of Argentina, each bone adds depth to the story of these early carnivores, reminding us that even the smallest details, like a pair of bony ridges, can illuminate the grand tapestry of life's ancient past. Part 20. Eoraptor. Eoraptor mogni inhabited the floodplain wetlands of what is now San Juan Province, Argentina, during the early Jurassic, around 200 million years ago. Its fossils were entombed in the red mudstones and siltstones of the Cañón del Colorado Formation, a landscape of braided rivers, seasonal lakes, and lush vegetation. Measuring roughly 3 meters from snout to tail and standing just over a meter at the hips, Eoraptor blended modest size with a long, graceful neck that inspired its name, far-eating lizard. Though it may not have dwarfed its later sauropod cousins, its combination of slender build and leaf-shredding dentition marked a key step in the transition from small, agile herbivores to the colossal, long-necked giants that would dominate the Jurassic. The story of Eoraptor's discovery began in 2009, when paleontologist Ricardo Martinez and his team unearthed 4 partial skeletons and 2 partial skulls near the tiny village of Mogna. Prior to this find, similar remains had been attributed to Massospondylus, but these new specimens revealed subtle anatomical distinctions, most notably a proportionally longer neck and evidence of keratinous beak structures at the jaw tips. By carefully comparing bone morphology and joint articulation, Martinez established Eoraptor as its own genus and species, underscoring the hidden diversity of early sauropodomorphs in southern Gondwana. Skull fragments of Eoraptor showcase a remarkable blend of primitive and derived traits. The snout was narrow and lightly built, ending in a sharp beak-like structure where keratin plates likely once covered the bone. Behind this were spoon-shaped teeth, each finely serrated for efficient cropping of plant material. Microscopic wear patterns on these teeth reveal both slicing and grinding motions, suggesting that Eoraptor could process both soft shoots and tougher foliage. A flexible lower jaw joint allowed lateral movement, further enhancing its ability to chew plant matter, a feeding adaptation that foreshadowed the sophisticated masticatory mechanisms of later herbivorous dinosaurs. Beneath the skull, the neck comprised at least 10 elongated cervical vertebrae, forming a gentle S-curve that allowed Eoraptor to reach high and low vegetation with ease. These vertebrae were lightly constructed, with complex air-filled cavities that reduced weight without compromising strength. The dorsal vertebrae transitioned into a robust sacrum fused to the pelvis, providing a sturdy platform for the hind limbs. Caudal vertebrae tapered gracefully toward the tail tip, their interlocking processes enabling both flexibility and balance. This axial skeleton reflects an evolutionary experiment in support and mobility, blending the needs of feeding range and locomotor stability. The forelimbs of Eoraptor were relatively short, but far from vestigial. Each arm ended in a hand with 5 digits, the first bearing an enlarged claw, likely used for grasping low branches or digging for roots. Muscle attachment scars on the humerus and ulna indicate sufficient power for deliberate movements, pulling vegetation closer or aiding in upright posture when feeding. In contrast, the hind limbs were long and straight, with a tibia slightly longer than the femur and an elongate metatarsus forming a digitigrade foot. These adaptations allowed swift, energy-efficient strides across shifting floodplain substrates, enabling Eoraptor to evade predators and migrate between feeding grounds. Dietary reconstructions position Eoraptor as a versatile herbivore capable of exploiting a range of plant resources. Its combination of beak and leaf-shedding teeth suggests an ability to nip off tender shoots and strip tougher leaves from branches. Pollen and spore data from the same formation indicate a flora dominated by tree ferns, horsetails, and early conifers, plants whose low and mid-level growth would have been readily accessible. Seasonal fluctuations in plant availability may have driven Eoraptor to occasionally supplement its diet with seeds or small invertebrates, as hinted by wear facets showing minor crushing action on some teeth. Bone histology of related early sauropodomorphs provides clues to Eoraptor's growth and metabolism. Rapid juvenile growth is marked by thick cortical bone and dense vascular networks, suggesting an elevated metabolic rate akin to warm-blooded animals. As individuals matured, bone tissue organization shifted toward more orderly lamellar structures, signifying a slowdown in linear growth once adult size was reached. This two-phase growth strategy, quick juvenile growth followed by stabilized adult maintenance, would have reduced vulnerability to predation while conserving energy in later life stages. Within its ecosystem, Eoraptor interacted with a suite of Triassic relics and Jurassic pioneers. Larger carnivores like Herrerasaurus and Colophysis prowled the same floodplains, likely preying on young or infirm individuals. Armored Dinosaurs and massive Dinosaurs browsed on coarser vegetation, while early pterosaurs flitted above. Eoraptor's intermediate size and bipedal agility allowed it to exploit foraging niches beneath tree canopies and along riverbanks, avoiding direct competition and predation through speed and widespread distribution. Phylogenetic analyses consistently place Eoraptor within Massospondyllidae, a clade closely related to Massospondylines and ancestral to true sauropods. Its unique combination of cranial beaks, specialized dentition, and mixed bipedal-quadrupedal tendencies highlights the mosaic evolution of feeding and locomotor adaptations. As a basal member of the group, Eoraptor embodies the early experiments that led to the colossal quadrupedal herbivores of the Jurassic. Its study continues to refine our understanding of how sauropodomorphs transitioned from small, agile bipeds to the iconic long-necked giants that reshaped Mesozoic ecosystems. Part 21. Ephrasia. Ephrasia minor emerged in the late Triassic floodplains of southwestern Germany, tracing its origins to roughly 210 million years ago. Its fossils, recovered from the Norian deposits of the Lowenstein Formation, paint a portrait of a lightly built herbivore skirting between bipedal and quadrupedal locomotion. Although juvenile remains suggested an initial length of 2 to 3 meters, adult specimens reached up to 6.5 meters, with thigh bones extending over 60 centimeters. This dramatic growth trajectory underscores the high metabolic rates and rapid bone deposition common among early sauropodomorphs, offering a window into the physiological strategies that would later fuel sauropod gigantism. The The skull of Eoraptor was small and triangular, perched atop a moderately elongated neck, composed of at least 9 cervical vertebrae. Its jaws bore a dental array of leaf-shaped teeth in the cheek region, ideal for cropping low-lying foliage, and conical premaxillary teeth at the snout tip that hint at occasional omnivory or selective feeding on tender shoots. Wear patterns on the tooth surfaces reveal both slicing and grinding motions, suggesting a versatile chewing cycle that processed fibrous plants efficiently. Such dental adaptability would have conferred resilience amid seasonal shifts in vegetation, allowing Eoraptor to exploit a broad spectrum of flora ranging from ferns to early gymnosperms. Hind limb anatomy illustrates a creature built for agile foraging rather than sustained speed. The femur and tibia are nearly equal in length, supporting a semi-erect stance that facilitated efficient walking and rapid short-distance sprints to evade predators or reach scattered food patches. The ankle joint exhibits a hinge structure optimized for digitigrade posture, ensuring each footfall conserved energy across uneven floodplain surfaces. Foot bones bear slender metatarsals terminating in 3 main toes with curved claws, providing traction in mud and over rocky substrates. This locomotor toolkit reveals a balance between stability during browsing and agility when threatened. Forelimbs of Eoraptor offer clues to its feeding and posture. Although shorter than the hind legs, the arms ended in hands with 4 functional digits, the first bearing an enlarged thumb claw. Muscle attachment sites on the humerus and scapula indicate moderate strength, likely employed for grasping vegetation, pulling down branches, or propping the body into a quadrupedal stance when feeding at ground level. Debates persist over whether these forelimbs could fully pronate the hands or merely provided light support, but the consensus places Eoraptor as an obligate biped when mobile, shifting to a semi-quadrupedal posture during feeding. The vertebral column of Eoraptor showcases both flexibility and lightness. Neural spines on the dorsal vertebrae are moderately tall, anchoring back muscles that held the torso aloft, while sacral vertebrae fused robustly to the pelvis to transmit hind limb forces. The tail vertebrae taper into a whip-like structure that acted as a dynamic counterbalance, aiding stability during locomotion and rapid turns. Pneumatic cavities within some vertebrae hint at early experimentation with air-filled skeletons, a trait that would become pronounced in later sauropods to reduce mass in massive bodies. Eoraptor inhabited a dynamic Norian ecosystem typified by braided rivers, floodplains, and ephemeral lakes. Seasonal monsoons delivered deluges that transformed grassy expanses into shallow wetlands, while volcanic ash from nearby eruptions blanketed the landscape, preserving bone beds rich in vertebrate remains. Coexisting herbivores included rhynchosaurs and other basal sauropodomorphs, while theropod dinosaurs and early crocodile relatives patrolled the same environments. Against this tapestry, Eoraptor's dietary flexibility and mixed locomotor abilities granted it access to both open and vegetated niches, reducing competition and enhancing survival. Bone histology reveals a 2-stage growth pattern: rapid juvenile deposition of fibrolamellar bone with few growth lines, followed by a transition to slower lamellar bone as maturity approached. This growth strategy, quick initial size gain followed by sustained adult maintenance, mirrors patterns seen in modern birds and mammals and underscores the elevated metabolic rates that early dinosaurs possessed. Such physiology allowed Eoraptor to reach reproductive age swiftly, reducing juvenile mortality and supporting population resilience in the face of environmental fluctuations. Phylogenetic analyses consistently recover Eoraptor as a basal sauropodomorph, more derived than the Codontosaurus, but less specialized than Plateosaurus or true sauropods. Its mosaic anatomy, primitive wrist joint, leaf-shredding teeth, semi-erect hind limbs, marks it as a transitional form, exploring both bipedal agility and quadrupedal browsing. This pivotal position offers crucial insight into the stepwise acquisition of traits that would culminate in the massive quadrupedal sauropods of the Jurassic, highlighting the evolutionary tinkering that characterized the dawn of herbivorous dinosaur dominance. Despite detailed study, many facets of Herrerasia's life remain enigmatic. No direct integument impressions have been found, leaving its skin covering speculative, simple scales, filamentous protofeathers, or a combination may have clad its frame. Social behavior is inferred from associated bone clusters, but lacks definitive trackway evidence of herd movements. Nesting strategies, parental care, and precise seasonal migrations await discovery of nests or juvenile accumulations. Each new fossil from the Norian beds of Germany holds the promise of illuminating these mysteries, further fleshing out the life portrait of this early herbivore, whose experiments in diet and locomotion helped shape the trajectory of dinosaur evolution. Part 22. Herrerasaurus. Herrerasaurus incertus strode across the floodplains of late Triassic Argentina, its chunky form cutting an unmistakable silhouette against the braided river channels of the Los Colorados Formation. Its name, lizard from La Rioja, pays tribute to the province where this prosauropod was first unearthed. Estimates place this dinosaur at anywhere from 6 to 10 meters in length, with a long neck and tail balancing its hefty body. Though not the tallest of its kind, Herrerasaurus stands out as one of the largest and most distinctive early sauropodomorphs to have ventured out of Gondwana's southern reaches. The initial skeletons of Herrerasaurus surfaced in 1966, when José Bonaparte led expeditions to a quarry near Villa-Unión. The holotype specimen included a postcranial skeleton missing only the skull, yet it preserved 6 presacral vertebrae, a suite of tail bones, both shoulder blades, the ischia, and hand bones. Over the next decades, at least 20 more individuals surfaced, ranging from juveniles to mature adults. A breakthrough came in 1995 when the first skull material was identified, confirming earlier inferences about its feeding apparatus and completing the puzzle of its cranial anatomy. Beneath its long, graceful neck lay a heavy torso supported by robust, pillar-like legs. Unlike many early sauropodomorphs, Herrerasaurus sported 4 sacral vertebrae fused to the pelvis instead of 3, providing extra strength for carrying its mass. Though its limb bones were dense and massive, its vertebrae were laced with hollow cavities that lightened the overall skeleton, a clever compromise between stability and weight savings. Its tail vertebrae tapered gradually into a whip-like extension used for dynamic balance during movement. Movement likely occurred in a slow, deliberate quadrupedal gait. The near equality in length between forelimbs and hind limbs suggests an obligatory 4-footed stance, a contrast to its bipedal ancestors. Hand bones show limited rotation, inconsistent with walking on clasped palms. Instead, Herrerasaurus seems to have supported its bulky frame on the outer edges of its hands. While capable of rearing onto its hind legs briefly, it appears that quadrupedality was its default mode, perhaps to maintain a low head position for feeding on wide swaths of ground vegetation. The skull of Herrerasaurus, once discovered, revealed a suite of features tailored for herbivory. A sharp beak-like front of the upper jaw helped nip off tender shoots, while leaf-shaped, serrated teeth lined the cheeks for efficient shredding of ferns and cycads. 5 teeth occupied the premaxilla, followed by over 20 cheek teeth tucked beneath the orbit. Wear patterns on the tooth enamel show both slicing and grinding marks, indicating a two-stage chewing cycle that both cut through tough fibers and further macerated plant tissues before swallowing. Herrerasaurus's world was one of shifting river channels, seasonal lakes and volcanic ash falls. Floodplain sediments preserved in vibrant reds and oranges now yield fossil beds rich in plant and animal remains. Alongside Herrerasaurus, smaller prosauropods, early theropods, and armored dinosaurs navigated this ever-changing terrain. Pollen and spore assemblages tell of a diverse flora: tree ferns, horsetails, and primitive conifers that covered the plains, providing an abundant buffet for plant-eating dinosaurs, while occasional droughts and volcanic eruptions sculpted the landscape and challenged its inhabitants. Bone histology hints at rapid juvenile growth in Herrerasaurus, with thick-walled bones reflecting swift early development to escape predation. As individuals matured, growth rates slowed and lamellar bone became more prominent, indicating a shift to energy allocation for maintenance rather than size increase. Comparisons of scleral ring morphology suggest this dinosaur may have been cathameral, active in short bursts throughout the day and night, an adaptation that maximized feeding opportunities while avoiding peak predator activity and midday heat. Phylogenetically, Herrerasaurus anchors the family. Herrerasauridae, closely allied with Melanosaurus of Southern Africa. This grouping sits near the base of Sauropodomorpha, highlighting a phase of experimentation in body plan and feeding strategies. Herrerasaurus's mix of primitive traits, such as a modest neck length and sizable forelimbs, and derived characteristics, like advanced sacral fusion and hollow vertebrae, shows how early sauropodomorphs gradually assembled the toolkit that would propel their descendants to colossal sizes. Its unique anatomy underscores convergent evolutionary pressures on herbivorous dinosaurs across Gondwana. Despite decades of excavation, Herrerasaurus still holds mysteries. No direct skin impressions have revealed whether it bore scales, protofeathers, or a blend of both. Its social structures, herding, solitary browsing, or seasonal migrations, remain speculative, though bone beds suggest some degree of group aggregation. Reproductive habits and nesting sites are unknown, awaiting discovery of eggs or juvenile clusters. Each new fossil from Argentina's Triassic beds promises to illuminate these facets, ensuring Herrerasaurus remains a keystone species in unraveling the saga of how small, agile-hipped ancestors gave rise to the towering, four-legged giants of the Mesozoic. Part 23. Lesothosaurus. Lesothosaurus diagnosticus, a nimble and lightly built dinosaur, thrived during the early Jurassic period roughly 200 million years ago. Its fossils have been uncovered in what is today the Kingdom of Lesotho in southern Africa, giving it its memorable name. This small ornithischian represents one of the earliest branches of the bird-hipped dinosaurs, offering a glimpse into the early evolution of a group that would later produce the likes of Triceratops and Stegosaurus. Lesothosaurus measured about 2 meters in length and stood no taller than a large dog, moving lightly across the landscape on its slender hind limbs. The skeleton of Lesothosaurus reveals an animal built for speed and agility. Its long, powerful legs and lightweight frame made it a consummate runner, a critical adaptation for an herbivore living alongside predatory contemporaries like Megapnosaurus. Its hind limbs were elongated, with a particularly strong femur and tibia, indicating powerful strides. The tail was stiffened by ossified tendons, acting like a balancing rod to stabilize the animal during rapid movement or tight turns. Its forelimbs, shorter than the hind limbs, were nevertheless flexible and ended in 5-fingered hands, which may have been used for manipulating vegetation. The skull of Lesothosaurus is a masterpiece of lightweight construction. It featured large eye sockets, suggesting excellent vision that likely helped in detecting predators. Its jaws were equipped with sharp, leaf-shaped teeth, ideal for slicing through tough plant material, and a beak-like structure at the tip of its jaws provided additional efficiency in cropping vegetation. The lower jaw could slide slightly backward, allowing a rudimentary form of chewing, a rare and advanced trait among such early dinosaurs. This capacity to chew made Lesothosaurus better equipped to digest a wide range of fibrous plants, giving it a flexible diet during seasonal changes. In terms of habitat, Lesothosaurus roamed an environment characterized by braided rivers, seasonal floods, and stretches of desert. The Karoo Basin, where its fossils were found, paints a picture of a dynamic landscape shaped by monsoonal rains and periods of intense aridity. Vegetation was dominated by conifers, cycads, and ferns, providing ample food sources. The semi-arid climate and shifting watercourses meant that resourcefulness was a key to survival, and Lesothosaurus's versatility as both a browser and a ground-level forager would have given it an advantage in this ever-changing world. Lesothosaurus's lightweight design and efficient feeding adaptations suggest that it was likely a solitary forager or moved in small, loose groups, rather than forming the large herds seen in later herbivorous dinosaurs. Its small size and quickness would have made tight social coordination unnecessary, and in fact, may have favored individuals spreading out to minimize competition for patchy food resources. Bone beds containing multiple individuals suggest occasional groupings, possibly during migrations or around shrinking waterholes during dry seasons. Bone histology studies show that Lesothosaurus grew rapidly in its early years, reaching near adult size within just a few years. This fast growth rate would have been an evolutionary response to high predation pressure, allowing juveniles to outgrow their most vulnerable stages quickly. The bone tissue also hints at periods of slower growth, perhaps tied to seasonal food shortages. The ability to flexibly adjust growth rates based on environmental conditions may have contributed to the species' persistence during times of climatic instability. The phylogenetic placement of Lesothosaurus has sparked considerable debate. Initially considered one of the most basal members of Ornithischia, it has sometimes been proposed to fall outside of the traditional clade entirely. Its mixture of primitive traits, like a simple pelvis structure, and advanced features, such as its jaw articulation and cheek teeth, suggest it occupied a key position close to the root of Ornithischian evolution. This mix underscores how early in their history, dinosaurs were still experimenting with different body plans and survival strategies. Interestingly, Lesothosaurus fossils often show signs of heavy wear on the teeth, implying that these dinosaurs lived long enough for such dental damage to accumulate. This wear could also indicate a diet that included gritty plants or occasional ingestion of sediment while grazing. Some scientists have even speculated whether Lesothosaurus might have been an opportunistic omnivore, snatching up small animals or insects when the opportunity arose, although its dental structure is most consistent with a primarily herbivorous lifestyle. Despite its relatively small size and unassuming appearance, Lesothosaurus stands as an important figure in dinosaur history. It bridges the gap between the earliest experimental forms and the highly specialized ornithischians that would later dominate Jurassic and Cretaceous ecosystems. Every fossil unearthed in the highlands of Lesotho is another thread to the rich tapestry of early dinosaur evolution, illustrating how, even in harsh and changing environments, adaptability, speed, and ingenuity paved the way for long-term success. Part 24. Guayabosaurus. Guayabosaurus candelariensis emerged in the Norian stage of the late Triassic, approximately 225 million years ago, along the braided river floodplains of what is now Rio Grande do Sul in southern Brazil. Its name, Guayaba lizard, honors the nearby Rio Guayaba basin, and the species epithet references the town of Candelaria close to its discovery site. Measuring roughly 2 to 3 meters from snout to tail and weighing perhaps 70 kilograms, Guayabosaurus combined a slender, lightweight frame with surprisingly robust skeletal features. Its presence so early in the dinosaur timeline makes it one of the most important organisms for unraveling how the two great Saurischean lineages, the carnivorous theropods and the plant-eating sauropodomorphs, first diverged and diversified across Pangaea's southern latitudes. The discovery of Guayabosaurus began in the late 1990s, when paleontologists exploring the Catarrita Formation's red mudstones near the town of Candelaria uncovered partial skeletons entombed in fine fluvial sediments. The first specimens included vertebrae from the back and tail, portions of the shoulder and pelvic girdles, and fragments of the hind limbs. A subsequent find yielded an almost complete hind limb, preserving tibia, fibula, and foot bones in articulation. These discoveries highlighted an ancient landscape that regularly flooded and rapidly buried animals in nutrient-rich mud, preserving their bones with remarkable fidelity. The abundance of specimens, several partial skeletons rather than isolated bones, allowed researchers to piece together a comprehensive view of Guayabosaurus's anatomy and lifestyle. Skeletal remains reveal a dinosaur of sweeping grace and surprising strength. The vertebral column shows a series of elongated back vertebrae leading into a long tapering tail stiffened by interlocking processes, which would have served as a dynamic counterbalance during agile movement. The shoulder girdle and forelimb bones, though not complete, indicate relatively short arms ending in hands with 3 functional fingers. In contrast, the hind limbs are long and slim, featuring a tibia slightly longer than the femur, an adaptation associated with rapid running. The foot bones culminate in 3 main toes tipped by strong claws, hinting that Guayabosaurus was well equipped to traverse variable Triassic substrates from muddy banks to firm gravel bars. Guayabosaurus's world was a tapestry of seasonal rivers, floodplain lakes and volcanic ash-laden plains. Conifer relatives, tree ferns and horsetails formed dense vegetation along riverbanks, while more open woodlands supported early synapsids and archosaurs. In this dynamic ecosystem, Guayabosaurus shared its habitat with small carnivores such as Styracosaurus and early sauropodomorphs like Saturnalia. Occasional volcanic eruptions blanketed portions of the landscape, leading to mass mortality events reflected in bone beds containing a mix of herbivores, carnivores, and omnivores. These ash layers, interbedded with mudstone, preserved snapshots of entire communities, capturing everything from microscopic pollen to articulated dinosaur skeletons with stunning clarity. The skull of Guayabosaurus remains unknown, but anatomical features of its jaws can be inferred from the shape of its premaxillar fragments and tooth impressions found nearby. It likely bore a slender, tapering snout with small, recurved, serrated teeth, ideal for grasping and slicing food. Rare root-like grooves on the jaw tips suggest the presence of a keratinous beak covering, enabling precise cropping of vegetation or small prey. Behind the beak, the cheek region housed teeth suited for processing plant fibers or soft animal tissue, supporting a flexible, possibly omnivorous diet. This combination of feeding adaptations underscores the experimental nature of early dinosaurs as they colonized a variety of ecological roles. One of the most debated aspects of Guaiabosaurus is its evolutionary placement. Initial studies proposed it as a very basal saurischian, perhaps ancestral to both theropods and sauropodomorphs, because it lacks the full suite of advanced traits seen in later dinosaurs. Some researchers have highlighted its primitive pelvis and only 2 sacral vertebrae, features more common in early meat-eaters, while others point to its leaf-shaped teeth and limb proportions as evidence of sauropodomorph affinities. Modern phylogenetic analyses generally nest Guaiabosaurus within Sauropodomorpha, often closely allied with Saturnalia and Chromogysaurus in the family, Guaiabosauridae. Yet its retention of theropod-like hind limb and hip characters keeps the debate alive. This mosaic anatomy makes Guaiabosaurus a living bridge across the early Saurischian divide. Understanding Guaiabosaurus's place in dinosaur evolution enriches our picture of how major lineages emerged. Its Norean age indicates that dinosaurs had already split into distinct evolutionary paths by the late Triassic, experimenting with both carnivorous and herbivorous lifestyles across Pangaea. By combining traits of both theropods and sauropodomorphs, Guaiabosaurus demonstrates that early dinosaur evolution was not a simple branching event, but a labyrinth of convergent and divergent adaptations. Each new anatomical insight, whether a previously unknown forelimb element or a fresh vertebral fragment, helps paleontologists refine the timeline and pace of dinosaur diversification. Future discoveries hold the promise of resolving lingering mysteries. A skull of Guaiabosaurus, if found, would illuminate its sensory capabilities and dietary preferences, clarifying whether it leaned more toward meat or plant consumption. More complete forelimb material could reveal whether it retained true bipedal running or began to experiment with quadrupedal browsing. Even additional embryonic remains might one day emerge, offering clues to its reproductive biology and growth patterns. Until those moments arrive, Guaiabosaurus remains both a testament to the ingenuity of early dinosaurs and a tantalizing enigma, reminding us that the dawn of Dinosauria was as complex and dynamic as the creatures it produced. Part 25. Pantidraco. Pantidraco caducus stands as a modest yet pivotal figure in late Triassic ecosystems. Its fossils preserved in the fissured mudstones of the Pantyfinnan quarry near Bonvilston in South Wales. The genus name Pantidraco, dragon of the spring hollow, honors the quarry's Welsh name, while the species epithet caducus, meaning fallen, alludes to how the animal's remains tumbled into natural sinkholes and fissures before fossilization. Discovered in the early 1950s and long mistaken for a juvenile the Codontosaurus, these bones only achieved their own identity in 2007. Though represented by a single partial skeleton of a young individual, Pantidraco's delicate yet telling anatomy illuminates a key transitional stage between carnivorous ancestors and the mighty herbivores that would later dominate Mesozoic landscapes. Anatomical features of this small dinosaur reveal a creature built for both nimble locomotion and versatile feeding. Its hind limbs are long and slender, with a tibia slightly exceeding the femur in length, an adaptation associated with quick, energy-efficient strides. The ankle joint allowed a digitigrade posture, elevating the foot to conserve energy and increase stride length. A long tail, stiffened by interlocking vertebral processes, acted as a counterbalance during rapid turns, while narrow hip bones anchored powerful thigh muscles. In contrast, the forelimbs were shorter but surprisingly capable, ending in hands with 3 functional fingers tipped by curved claws, suggesting Pantidraco could grasp small branches or manipulate objects as part of its foraging behavior. Pantidraco's skull, though only partially preserved, hints at a feeding apparatus in flux. The front of the jaws likely bore a narrow predentary beak, capable of cropping tender vegetation, while the cheek region included small leaf-shaped teeth marked by fine serrations. Microwear studies on related prosauropods show a mix of slicing and grinding marks, and Pantidraco's dentition suggests a similar dietary flexibility, primarily herbivorous but also opportunistically omnivorous when invertebrates or small vertebrates were available. Such a mixed feeding strategy would have been advantageous in the fluctuating climates of the Ratian stage, when seasonal droughts and floods altered plant communities dramatically. The quarry deposits that yielded Pantidraco's remains formed in a low-lying wetland environment, where rivers and streams meandered across broad floodplains. Periodic monsoonal rains inundated these plains, depositing fine silts that would later encase the bones of drowned animals. Between the flooding episodes, the landscape supported a mosaic of tree ferns, horsetails, and early conifers, forming lush undergrowth ideal for small browsing dinosaurs. Bone beds from the same strata also preserve armored reptile fragments and amphibian remains, indicating a complex web of co-occurring fauna. Within this tapestry, Pantidraco moved quietly through the underbrush, its keen senses alert for both food and lurking predators. Growth studies of juvenile bones from Pantidraco show rapid early development, with thick, vascularized cortical bone indicating high metabolic rates and fast growth to reduce predation risk. As the animal matured, bone deposition slowed and more organized lamellar tissue appeared, suggesting a shift in energy allocation from size increase to maintenance and reproductive readiness. This two-phase growth pattern mirrors trends seen in both later sauropodomorphs and modern endothermic vertebrates, underscoring that elevated metabolic strategies emerged early in dinosaur evolution to support active lifestyles and resilience in unpredictable environments. Phylogenetic analyses consistently place Pantidraco among basal sauropodomorphs, the group that would eventually give rise to the giant, long-necked sauropods of the Jurassic and Cretaceous. Its blend of primitive traits, such as a relatively gracile limb skeleton and derived features, like the presence of a predentary beak and leaf-shredding cheek teeth, highlights the mosaic fashion in which sauropodomorph characteristics accumulated. Pantidraco thus occupies a key node in the dinosaur family tree, illustrating how initial dietary and locomotor innovations set the stage for the later evolution of colossal quadrupedal herbivores. Despite being known from only one partial skeleton, Pantidraco's importance extends far beyond its modest remains. It exemplifies the transitional experimentation that characterized the earliest phases of dinosaur diversification, when lineages explored new feeding strategies and locomotor repertoires. This small Welsh dinosaur helps bridge the morphological gap between carnivorous ancestors, whose descendants would dominate as theropods, and the later obligate herbivores, whose bulk reshaped Mesozoic ecosystems. Every new detail gleaned from Pantidraco's bones brings paleontologists closer to understanding the gradual, stepwise unfolding of dinosaur adaptation. Yet many mysteries linger around Pantidraco. The absence of adult specimens leaves us to infer how large this species truly could grow, and whether its proportions shifted markedly with age. No direct skin or soft tissue impressions have been found, leaving its integument scaly, filamentous, or a combination, purely speculative. Likewise, its social behavior remains an open question. Did it forage alone, or did small family groups patrol the wetlands together? Future discoveries in the Carboniferous limestone casts beneath southern Wales may one day answer these questions and unveil new chapters in the life story of this diminutive dragon of the Triassic.